Hey everyone, and welcome back to Echoes of the Unknown. Tonight we re-peeling back the layers on what might be the single most compelling piece of evidence that we are not alone in the universe. We're talking about a signal that lasted for just 72 seconds, was never heard again, and was so powerful, so strange, that the astronomer who found it could only write one word in the margin of the data printout. Wow, what if the most important message in human history wasn't a grand arrival, but a fleeting whisper from the void, caught by accident on a summer night? Before we dive into the mystery, if you're as fascinated by the unknown as I am, please hit that like and subscribe button. It helps us find more stories that deserve to be told, and we want to hear from you. Drop a comment below with a mystery you think is due for a new look. All right, turn down the lights, get comfortable, and let's begin our investigation. You are standing in a field in central Ohio. The date is August 15th, 1977. It's a warm, humid summer night, the kind where the air is thick and heavy, smelling of damp earth and distant cornfields. Above you, a vast star-dusted sky is just beginning to reveal its full splendor as the last vestiges of twilight fade from the western horizon. The only sounds are the rhythmic chirping of crickets and the rustle of leaves in a gentle breeze. It's a scene of profound peace, a tableau of rural America untouched by the noise and hurry of the city. But here, in this quiet field near the town of Delaware, you see something that doesn't belong. It's a colossal structure, a silent mechanical giant sprawled across the landscape. It isn't a gleaming, futuristic dish like the ones you might see in movies. Instead, it looks more like a gargantuan piece of industrial scaffolding, a massive fixed wall of wire mesh, a parabolic reflector, as big as 3 football fields laid end to end. Some distance away, you see another, smaller reflector, this one capable of tilting. This is the Ohio State University Radio Observatory, known affectionately to its staff as the Big Ear. Tonight, like every night, the Big Ear is listening. It is a sentinel, patient and unmoving, its gaze fixed upon the heavens. But its eyes are not optical. It sees in radio waves, the invisible light that permeates the cosmos, carrying stories of dying stars, swirling galaxies, and the cold background hum of the universe's birth. Its primary mission, funded by a shoestring budget and run by a small dedicated team and a handful of passionate volunteers, is to map the radio sky, to create a comprehensive survey of celestial objects emitting in these wavelengths. But it has a secondary, more profound and perhaps more hopeful purpose: to listen for any signal that might betray the existence of intelligence beyond our world. It is a part of the nascent and often ridiculed search for extraterrestrial intelligence, or SETI. It's now 10:16 p.m. Eastern Daylight Time. No one is here. The observatory grounds are deserted. The scientists and engineers have gone home for the day. There is no bustling control room, no one in a lab coat hunched over a console, waiting for a cosmic telephone to ring. The entire operation is automated, a ghost in the machine running its nightly course. The Big Ear doesn't move. Its genius lies in its stillness. It uses the rotation of the Earth itself as its mechanism for scanning the sky. As our planet spins on its axis, new slivers of the cosmos drift through the telescope's narrow field of view. At this precise moment, a patch of sky in the constellation Sagittarius is gliding into focus. It's a busy, glittering neighborhood of the Milky Way, located near the dense, star-packed galactic center. And from somewhere within that celestial tapestry, a signal is arriving. It has been traveling for an unknown amount of time, crossing an unimaginable expanse of empty space. It is impossibly faint, a whisper carrying just a few zeptawatts of power, an amount of energy so minuscule it's difficult to comprehend, yet it is here. It slices through Earth's atmosphere, unimpeded, and strikes the vast collecting area of the Big Ear. You can almost feel the moment of contact. The radio waves, vibrating at a very specific frequency, are focused by the huge reflectors onto 2 horn-shaped receivers. From there, the whisper from Sagittarius is transformed. It becomes a weak electrical current, an ordered stream of information that is amplified millions of times. This current flows through shielded cables into a small, unassuming trailer that serves as the observatory's control room. Inside, the air is cool and smells of ozone and warm electronics. The only sound is the low hum of cooling fans and the rhythmic clatter of a machine. The signal, now a robust stream of data, is fed into an aging IBM 1130 mainframe computer. The computer does what it's programmed to do. It measures the signal strength 60 times a minute for each of the 50 channels it's monitoring. It then translates these measurements into a simple code, a number from 1 to 9 for weak to moderate signals, and then, if the signal's intensity continues to climb into truly exceptional territory, it uses the letters of the alphabet, from A to U, to represent ever-increasing power. The number 0 represents the baseline, the background noise of space. A blank space means no signal at all. A teletype printer begins to chatter, mechanically punching these characters onto a continuous sheet of fan-fold computer paper. Column after column of numbers and letters march across the page, a raw, unfiltered transcript of what the big ear is hearing. And buried within this cascade of data, a sequence begins to print that has never been printed before. 6EQUJ5. The sequence appears, stark and anomalous, in a single column out of 50. The printer continues its work. The paper continues to spool out, filled with the usual, meaningless static of the cosmos. The moment passes. The Earth continues to turn, and the mysterious source in Sagittarius drifts out of the big ear's line of sight. The signal is gone. It was there for just 72 seconds, the exact amount of time it should take for a fixed celestial object to pass through the telescope S-beam. The printout, containing perhaps the most significant artifact in the history of astronomy, simply falls into a collection box with the rest of the night's data. It will sit there, unexamined, for days. No alarms have sounded. No pagers have gone off. The world is completely oblivious. You are left in the quiet Ohio night, under the shadow of the silent telescope, with a profound question hanging in the air. What if the most profound message in human history arrived when no one was there to hear it, recorded not with a bang, but with the quiet clatter of a machine printing a secret onto a forgotten page? You are still in that Ohio field, the crickets still singing their nightly chorus. The initial awe of the structure's sheer size begins to give way to curiosity. You want to understand this machine, this silent listener that, unbeknownst to the world, has just intercepted a message from the stars. You find yourself walking closer, tracing its perimeter in the dim moonlight. This isn't just a piece of equipment, it's an environment, a landscape reshaped for a single audacious purpose. This is a Krauss-type telescope, an ingenious design named after its creator, Dr. John D. Krauss, the visionary director of the observatory. You can see his philosophy etched into its very construction: achieve the grandest scientific goals with the simplest possible means. In an age of gleaming billion-dollar scientific instruments, the big ear is a monument to function over form, a testament to what can be accomplished with clever engineering and a lot of corrugated aluminum. Your walk takes you first to the smaller of the two main components, a massive, flat wall of wire mesh angled towards the sky. This is the tiltable reflector. It stands over 100 feet tall and 360 feet wide, a giant rectangular mirror for radio waves. You notice the heavy-duty mechanisms at its base, thick gears and motors that allow this entire wall to be slowly tilted up or down. This is the telescope's only means of aiming along the north-south axis, allowing the observers to choose a specific strip of sky, a particular declination, for their nightly vigil. For the past few years, its aim has been methodically adjusted, night after night, as part of the Ohio Sky Survey, its primary mission to create the most detailed map yet of the radio universe. From here, you turn and look across a vast open space, several hundred feet across, to the second, even larger component. It's the parabolic reflector, and it truly dominates the landscape. It's a fixed, unmoving structure, a curved wall 70 feet high and stretching for an incredible 700 feet. It looks like a colossal unfinished billboard waiting for an advertisement of cosmic proportions. Its surface is a precisely engineered curve, a perfect parabola designed to catch any wave bouncing off the flat reflector and focus it with unerring accuracy. You start to piece together how it works. You imagine the faint radio signal arriving from Sagittarius. It first strikes the flat tiltable reflector. From there, it is bounced across the field to the giant curved wall. This second collision is where the magic happens. The vast collecting area of the parabola gathers all the scattered faint energy of the signal and focuses it, concentrating it down into a single intense beam, like a magnifying glass, focusing sunlight onto a single point. The big ear's size isn't for show, it's for sensitivity. In the business of listening for whispers from across the galaxy, the bigger the ear, the better. But where does that focused beam go? You follow the geometry in your mind and realize the focal point isn't in the air. It's directed down into the ground itself. You walk to the base of the huge curved wall and find what you're looking for. A long, concrete-lined trench running along the reflector's base. You peer inside. Down in this channel, protected from the elements and stray radio noise, are the true hearts of the telescope. Two large, horn-shaped receivers. These horns, looking like primitive megaphones, are where the radio waves finally end their journey. They funnel the focused energy into the sensitive electronics that will convert the wave into a data stream. The telescope had two horns to scan adjacent patches of sky simultaneously. A clever trick that helped astronomers distinguish a true celestial signal from random terrestrial noise. As you look around, you become aware of the ground beneath your feet. It's not just dirt and grass. You notice the surface is dark, unusually uniform. This isn't a simple field. It's a critical component of the telescope. You're standing on a specialized ground plane, an asphalt surface coated with a specific material that absorbs stray radio waves rather than reflecting them. Dr. Krauss and his team knew that any unwanted reflections from the ground could create interference, ghost signals that could ruin their observations. So they paved a massive portion of this Ohio farmland, turning the very earth into a shield against noise. It's a detail few would ever notice, but it speaks volumes about the meticulous care that went into the Big Ear's design. Every element was considered in the quest for a clear, clean signal. The telescope's design is a paradox. Its stationary nature makes it seem primitive, even obsolete, compared to the fully steerable dishes that were becoming the standard in radio astronomy. Those modern telescopes could be pointed anywhere in the sky at a moment's notice, tracking objects with precision. The Big Ear could only watch as the universe drifted by. It was patient, methodical, and slow. Its view was dictated not by an astronomer at a console, but by the relentless, silent turning of the Earth. Yet its sheer size gave it a sensitivity that smaller, more agile dishes couldn't match. It traded speed for power. And this brings a critical question to your mind as you stand there in the dark, contemplating this strange and wonderful machine. Could this perceived weakness have been its greatest strength? A modern telescope, with its busy schedule, might have been aimed at that exact spot in Sagittarius for only a few minutes before moving on to its next target. It would have missed the 72-second signal entirely. The Big Ear, however, was built for long stares. Its slow, sweeping gaze, a consequence of its outdated design, made it uniquely suited to catch a transient event, a one-time-only broadcast. Could it be that in our rush to build faster, more agile instruments, we risk losing the very patience required to hear a voice that speaks only once? Perhaps this silent giant, rusting away in a quiet Ohio field, was the perfect trap for the perfect signal. A cosmic encounter engineered by chance and stillness. The scene shifts. Several days have passed since that quiet, humid night. The Earth has continued its silent spin, and the Big Ear has continued its patient vigil, spooling out miles of paper filled with the mundane chatter of the cosmos. The printout from the night of August 15th is no longer in the collection box at the observatory. It's part of a thick, heavy stack, sitting in the back of a car making its way through the late summer landscape of central Ohio. You are now looking at the man behind the wheel. He is not what you might picture when you think of a figure at the center of a potential first contact scenario. There is no gleaming lab coat, no air of dramatic importance. He is Dr. Jerry R. Amon, a man in his late 30s with a calm, thoughtful demeanor. He is an associate professor of astronomy, but his work here with the Big Ear is entirely voluntary. This isn't his day job. This is his passion. Like a handful of others, he has dedicated his free time to this monumental and often thankless task, sifting through the haystack of cosmic noise for the glint of a single intelligent needle. His routine is simple. Every few days, he drives to the Perkins Observatory, where the Big Ear's offices are located, and picks up the latest batch of data. He is one link in a chain of volunteers who share this responsibility. It could have been anyone's turn this week. A different volunteer might have collected this particular stack of paper. A different set of eyes might have been the first to scan these specific columns of data. It is a detail that feels small, a simple matter of scheduling, but you sense a profound "what if" hanging in the air. The universe, it seems, relies as much on chance and circumstance as it does on physics. Jerry Amon is uniquely suited for this task. His background isn't just in general astronomy. He has deep expertise in the complex world of radio telescopes, signal processing, and crucially, the myriad forms of radio frequency interference. He knows what a satellite looks like as it passes overhead. He knows the signature of a distant thunderstorm, the telltale signs of a faulty piece of electronics, or the interference from a passing truck with a noisy ignition system. His mind is a finely tuned filter, trained to recognize and discard the endless stream of imposters and ghosts that can mimic a signal from deep space. He is not just looking for a signal. He is looking for a signal that cannot be explained away by any earthly or natural means. You follow him as he arrives home. The stack of fanfold paper is heavy in his arms. It's not a single sheet, but a continuous ream, thousands of pages long, representing every second of the observatory's listening time. You can almost smell the unique scent of the paper and the slightly acrid ink from the dot matrix printer. In his study, a sanctuary of books and academic papers, he settles into his chair. The task before him is a form of meditation, a slow, methodical journey through raw information. You watch as he begins to scan the pages. His eyes move with practiced efficiency, flowing down the 50 columns of data. Blank space, 1, 2, 1, blank space. This is the norm. The vast majority of what the Big Ear records is nothing, the whisper-quiet background temperature of the universe. Occasionally, a higher number appears, a brief flicker of natural radio emission from a distant quasar or a pulsar. But these are known entities, familiar friends to a radio astronomer. He is looking for the stranger, the anomaly, the pattern that breaks the pattern. It is a task that would drive most people to madness with its monotony, page after page of near-identical data, a river of cosmic static. But for Amon, and the other volunteers like him, there is a quiet hope that fuels the effort. The hope that on one of these pages, buried in one of these columns, will be the proof they are all looking for. It is a search driven by one of the most fundamental questions of human existence. Are we alone? To answer it, or even to find a clue, is worth 1,000 hours of tedious, eye-straining work. He isn't just looking for a strong signal. Strength alone can be caused by interference. He is looking for a specific profile. A true celestial signal should appear in only one of the two receiver horns at a time. It should rise in intensity, peak and then fall, a perfect bell curve lasting for exactly 72 seconds as the Earth's rotation sweeps the source through the telescope's beam. And it should be narrow band, confined to a single sharp frequency, a hallmark of an artificial transmission unlike the broad, messy signals produced by natural phenomena. He is holding a mental template of an alien signal, a ghost he is trying to match against the reality of the data. You can sense the weight of the odds against him. The SETI project at Big Ear has been running for 4 years, and in all that time, they have found nothing. Not a single signal has passed all the rigorous tests to be considered a candidate. The universe has remained stubbornly, profoundly silent. There is no reason to think that this stack of paper, this particular week in August, will be any different. And as you watch him flip through another page, a critical question begins to form in your mind. A question that extends far beyond this one desk in Ohio. This entire discovery hinges on a volunteer, on his specific expertise, and his willingness to perform a monotonous task with unwavering diligence. It makes you wonder, how many other discoveries and how many other fields of science have been missed? How many revolutionary anomalies are lying dormant in unexamined data sets overlooked because no one had the time to look, or because the person who did look didn't have the unique combination of knowledge and intuition to recognize what they were seeing? What other wonders has the universe shown us, only to have them end up lost in a stack of paper? waiting for the right pair of eyes that may never arrive. You are in the room with him, a silent observer to a potentially historic moment. The air in Jerry Amon's study is still and quiet. The only sound, the soft rustle of paper as he pulls another long, fan-folded sheet across his desk. His focus is absolute. By now, he has been at this for some time and the rhythm of the work has taken over. Scan, process, dismiss, turn the page. Scan, process, dismiss, turn the page. You can feel the hypnotic effect of the endless columns of data. It is a world of ones, twos, and blank spaces, a digital representation of an empty and silent cosmos. His eyes, trained by years of this exact work, glide over the printout from August 15th. The data is organized by right ascension, the east to west coordinate of the sky. As he moves from one page to the next, he's effectively watching the telescope's field of view sweep across a continuous strip of the heavens. He passes through the data corresponding to 19 hours, 20 minutes of right ascension. Nothing. He continues to 19 hours, 21 minutes, still nothing but the faint, background murmur of the universe. Then his hand stops, his eyes freeze. Something has broken the pattern. It's on the left side of the page, just a few columns in. In a sea of low numbers, a sequence leaps out. It's not just one strong digit, but a cascade. It doesn't make sense. His mind, so accustomed to the static, registers it first as a mistake, a glitch in the machine. A smudge of ink, perhaps, or a momentary electronic hiccup that caused the printer to spit out gibberish. That would be the logical, the scientific explanation. His training immediately kicks in, his internal skeptic taking control. He leans closer, his brow furrowed in concentration. You can read the characters over his shoulder. 6EQUJ5. He forces himself to be methodical. First, check the basics. Is it just this one column? Yes. The adjacent columns, representing different frequency channels and the second receiver horn, show nothing but the usual low-level noise. This is significant. Terrestrial interference, like a passing aircraft or a military radar test, would almost certainly be broad enough to show up in multiple channels, and would likely be detected by both of the telescope's receiver horns. This anomaly is sharp, precise, and confined to a single horn and a single narrow channel. The first and most obvious explanation is already on shaky ground. Next, he considers the profile of the signal. His eyes trace the sequence not as individual characters, but as a progression, a story told over time. The signal appears with an intensity of 6, already more than 6 times the background noise. In the next measurement, it jumps to E, representing an intensity of 14, then Q, a staggering 26 times the background. The peak is U, a value of 30, the highest intensity the computer's software was programmed to represent with a character. For that brief moment, the signal was more than 30 times stronger than the deep space noise surrounding it. After this incredible peak, it begins to fade, but in a beautifully symmetric way. J, 19 times, then 5 times, before disappearing back into the noise. You can almost see the gears turning in his mind. This isn't a chaotic glitch. This is a perfect bell curve. It's a textbook example of what a signal from a fixed point source in deep space should look like as the Earth-ES rotation sweeps it through the big ear as narrow beam. The rise, the peak, the fall, it all happens over a duration of 72 seconds. Exactly the time it should take. The signal's behavior perfectly matches the telescope's known transit time. It's behaving precisely as if it were a radio transmitter attached to a distant star. The evidence against a simple error is mounting, and you can sense a shift in his posture, a change in his breathing. The initial skepticism is being eroded by the sheer perfection of the data. He checks the coordinates. Right ascension, 19 hours, 22 minutes, 24 seconds. Declination, 27 degrees, 3 minutes. It's a patch of sky in the northwestern corner of the constellation Sagittarius, near a globular star cluster known as M55. There are no known planets in that direction, no obvious powerful astronomical sources that could produce such a signal, and most importantly, it's far from the ecliptic plane, the highway where satellites, asteroids, and planets travel, making a reflection off a piece of space junk incredibly unlikely. Every logical door he tries to open, every conventional explanation he reaches for, is slammed shut by the data itself. The signal is strong. It is narrowband. It comes from a single point in the sky. It has a perfect rise and fall profile that matches the telescope's observational window. It doesn't look like interference. It doesn't look like a known natural phenomenon. It looks artificial. You watch as a wave of feeling washes over him, a complex cocktail of shock, disbelief, and electrifying excitement. This is the moment every SETI researcher dreams of and never truly expects to happen. It's the ghost in the machine made real. For a few long seconds, he just stares at the 6 characters on the page. 6EQUJ5. It's a code, a name, a cosmic license plate of unknown origin. It is a profound and unsettling artifact. He reaches for a pen, not a black or blue one for making routine notes, but a red one. The color of emphasis, of alarm, of discovery. With a hand that you imagine is not entirely steady, he draws a circle around the 6 characters, isolating them from the rest of the data, enshrining them. And then, in the left margin, next to the circled anomaly, he uncaps the pen and writes a single, 3-letter word. It is not a scientific notation, not a technical assessment. It is a pure, unvarnished, human reaction to confronting the utterly inexplicable. He writes, "Wow." The ink sinks into the paper and the word hangs there, a testament to a moment of genuine awe. You are left staring at that page, at that red circle and that simple, powerful word. And you can't help but wonder, what is that moment truly like? What is the emotional and intellectual process of confronting a piece of data that seems to tear a hole in your understanding of the universe? A piece of data that whispers of a possibility so profound it can change humanity forever? You are still staring at the page, the red circle a focal point in a sea of monochrome data. The word "wow" echoes in your mind, a perfect summary of the initial shock. But now the scientist's curiosity takes over, both in Jerry Eamon and in you. You want to move beyond the awe and get to the truth encoded in those 6 simple characters, 6EQUJ5. It's a language you don't yet speak, a code that holds the key to the signal's true power. Let's decipher it together. The system the Big Ear's computer used was both simple and elegant. Every 12 seconds, the computer would take a snapshot of the signal intensity for each channel. This intensity was measured as a signal-to-noise ratio, or SNR. You can think of it like this. Imagine you're trying to listen to a single flute in the middle of a roaring football stadium. The roar of the crowd is the background noise of the universe, a constant random hiss of energy left over from the Big Bang and from countless distant stars. The sound of the flute is the signal. An SNR of 1 would mean the flute is exactly as loud as the crowd. You might just be able to pick it out, but it's difficult. An SNR of 5 means the flute is 5 times louder than the crowd. An SNR of 30 means the flute is piercingly clear, cutting through the din with absolute authority. The computer then converted this SNR number into a single character to print on the page. A blank space meant no signal, an SNR of less than 1. The numbers 1 on through 9 were used for SNRs of 1 up to 10. So, a 1 was a faint whisper, a 5 was a clear note, and a 9 was a very strong signal, already an exciting find for any SETI researcher. But what if the signal was even stronger than 9? For that, the programmers turned to the alphabet. The letter A represented an SNR of 10 to 11. B was 11 to 12, C was 12 to 13, and so on. It was a compact, clever way to represent a huge range of possible signal strengths on a simple printout. With this key in hand, the true meaning of 6EQUJ5 begins to unfold, and you realize just how inadequate the word "wow" truly is. Let's look at the first character, 6. The signal appears from the noise, already at an intensity between 6 and 7 times the background. In the world of SETI, this alone would be enough to merit a second look. It's a clear, unambiguous detection. 12 seconds later, the next character is printed, E. Using the alphabet key, you count A, B, C, D, E. E is the 5th letter. This corresponds to an SNR between 14 and 15. The signal's strength has more than doubled in just 12 seconds. It's climbing, and it's climbing fast. The flute is getting louder, its note becoming sharper and more defined against the stadium's roar. The third character is Q. You trace your way through the alphabet. Q is the 17th letter, meaning the signal strength is now a staggering 26 to 27 times the background noise. This is far beyond any random fluctuation or the signature of most natural objects. This is a blast of energy, incredibly focused and incredibly powerful. And then comes the peak, U, the 21st letter of the alphabet. This represents an SNR of 30 to 31. The signal at its most intense was over 30 times more powerful than the combined radio noise of the cosmos in that direction. The flute is no longer a flute. It's a siren, a blaring, impossible note that drowns out everything around it. But here you notice a crucial and lesser-known detail. When you look at the observatory's documentation, you discover something fascinating about the computer's software. The programmer who wrote the code decided that a signal 30 times the background noise was so unlikely, so far beyond the realm of possibility, that there was no need to go any further. The alphabet scale stops at U. U was the highest value the system could possibly display. You realize the breathtaking implication. The signal may have been even stronger. It didn't peak at U. It was simply measured as U. The signal had, for all intents and purposes, maxed out the instrument. It was a shout so loud that the microphone clipped, unable to register its true volume. We will never know the signal's actual peak intensity, only that it was, at a bare minimum, an incredible 30 SNR. After this monumental peak, the signal begins to fade, just as symmetrically as it arrived. The fifth character is J, the 10th letter, corresponding to an SNR of 19 to 20. Even as it recedes, it is still more powerful than almost any other signal the observatory had ever recorded. Finally, the last character is 5, an SNR of 5 to 6. The source is now at the edge of the telescope's beam. 12 seconds later, it's gone. The column on the printout returns to blank spaces and the occasional 1 or 2. The stadium roar is all that's left. The flute has fallen silent. You lean back, the full weight of the data settling in. 6EQUJ5 is not just a random code. It is a perfect story, an astronomical narrative with a beginning, a middle, and an end, told over 72 seconds. It describes an object of immense power appearing out of the void, screaming its presence, and then disappearing just as cleanly as it came. And it raises a subtle but profound question. Our understanding of this event is entirely shaped by the tool we use to measure it. The arbitrary decision of a programmer in the 1970s to stop their measurement scale at the letter U has placed a permanent veil over the true nature of this signal. It makes you wonder, how does our choice of measurement and notation limit our perception of an event? And what might we have missed because our tools weren't built to comprehend the true scale of what they were seeing? What other truths about this cosmic whisper are lost forever, simply because we didn't know we needed a bigger alphabet? The meaning of 6EQUJ5 now burns in your mind. The sheer raw power of the signal is almost incomprehensible, but as you continue to analyze the printout alongside Jerry Amon, you realize there is another piece to this puzzle, a detail that might be even more profound than the signal's strength. It's not just what the signal said in the language of intensity, but where on the vast radio dial it chose to speak. Imagine the radio spectrum as a piano keyboard of immense, almost infinite length. Most of it is filled with noise, the chaotic crashing of chords from natural phenomena like star births, supernovas, and the radiation from black holes. Finding a clear, intelligent signal in that cosmic cacophony is a monumental challenge. So if you were trying to send a message to another species across the galaxy, you wouldn't just choose a random key to play. You would choose a special key, a universal note that you could be confident any other intelligent species would also recognize as significant. You look at the notes on the big ear printout. The signal, the incredible 6EQUJ5 sequence, was detected in the second of the 50 channels the telescope was monitoring. Amon checks the frequency corresponding to that channel. The number he finds is chilling in its perfection: 1420.45I5E6 megahertz. To a layperson, that number is meaningless. To an astronomer, it is resonant with meaning. It is almost exactly the frequency of the hydrogen line. To understand why this is so important, you have to think about the universe at its most fundamental level. The most common, the most simple, the most widespread element in the entire cosmos is hydrogen. It was the first element forged in the Big Bang, and it makes up more than 90% of all the atoms in the universe. It is the primary fuel of stars, the stuff of nebulae, the elemental building block of everything. Any civilization capable of building a radio telescope would, by necessity, have a deep understanding of physics and chemistry. They would know and understand hydrogen. And hydrogen, in its neutral state, does something remarkable. The single electron orbiting the single proton can exist in two energy states depending on its spin. Every so often, on a timescale of millions of years for a single atom, that electron will spontaneously flip its spin to the lower energy state. When it does, it releases a tiny, almost imperceptible packet of energy in the form of a radio wave. A radio wave with a very, very specific frequency, 1420-405-75 megahertz. This is the hydrogen line, sometimes called the 21-centimeter line. It is a fundamental constant of nature, woven into the very fabric of the universe. It is a universal signpost. It's the X on the cosmic treasure map. In 1959, physicists Philip Morrison and Giuseppe Cocconi published a landmark paper in the journal Nature, proposing that if we were to search for alien signals, the hydrogen line was the most logical place to look. It was, they argued, the one channel that any intelligent species, regardless of their biology or homeworld, would surely know about. This is why Eamon and his colleagues had tuned the big ears receivers to listen to this specific part of the radio spectrum. And this is why the discovery of a powerful structured signal at this exact frequency is so electrifying. It's as if you had agreed to meet a stranger in a vast, unfamiliar city, with the only instruction being to meet at the most famous landmark. You arrive at the Eiffel Tower, and there, at the prearranged time, is a person waiting, looking for you. The wow signal didn't just shout. It shouted from the most logical, most anticipated lighthouse in the entire cosmic ocean. But there's more. Here you uncover a lesser-known, more technical detail that strengthens the case for the signal's artificiality. The big ear wasn't just staring at the hydrogen line itself. It was monitoring a 500 kilohertz band of the spectrum around that line, divided into 50 narrow channels, each just 10 kilohertz wide. Natural phenomena are messy. They tend to broadcast energy over a wide range of frequencies like a shotgun blast. If the wow signal had been a natural event, you would expect to see its energy smeared across several of those 50 channels. You look back at the printout. The 6EQUJ5 sequence appears only in column 2. The columns on either side, column 1 and column 3 representing the adjacent frequency channels, are quiet. They show nothing but the usual background noise. This means the signal was narrow band. It was a pure, focused tone, confined to a sliver of the spectrum less than 10 kilohertz wide. To use the sound analogy, it wasn't a roar, it was a whistle. This is the hallmark of an artificial signal. It takes technology to concentrate that much energy into such a narrow frequency band. Nature doesn't work that way. The pieces are all falling into place, each one more compelling than the last. An incredibly powerful signal, with a perfect rise and fall profile from a fixed point in the sky, at the most logical frequency for interstellar contact, and with a narrow band signature that is exceptionally difficult to explain through natural causes. Yet, this very logic presents you with a haunting paradox. You are now contemplating what astronomers call the cosmic waterhole, a quiet patch of the spectrum, ideal for communication situated right next to the hydrogen line. The name itself evokes an image of a gathering place for all the diverse life of the galactic savanna. But as you look out from this spot, you see no one. The waterhole is silent. For decades, we have been listening here, and we have heard nothing but this one solitary 72-second shout that was never repeated. This forces you to ask a difficult question. If this frequency is so obvious, so logical for a galactic conversation, why is it so eerily quiet? Could our very assumption that it's the universal hailing frequency be a form of anthropocentric thinking, a projection of our own logic onto a universe that operates by completely different rules. We may have shown up at the Eiffel Tower, but perhaps everyone else in the city agreed to meet at the Arc de Triomphe instead, and we are left waiting alone, clutching a single mysterious 40-year-old postcard. You now have two powerful pieces of evidence laid out before you: the signal's staggering intensity and its profoundly significant frequency. Each one, on its own, would be a remarkable discovery. Together, they form a compelling case for something extraordinary. But there is a third pillar supporting this mystery, one that is tied directly to the unique design of the Big Ear telescope itself. The signal's duration, the length of time it was heard. You turn your attention back to the mechanics of the observatory. Remember, the Big Ear was a stationary instrument, a passive observer that let the universe come to it. Its view of the cosmos was a narrow, vertical slit. As the Earth spun on its axis, this slit would sweep across the sky like a scanner bar, observing anything that drifted through it. The physics of this arrangement were precise and predictable. Given the width of the telescope's beam and the speed of the Earth's rotation, any object fixed in deep space, a distant star, a nebula, or a hypothetical alien transmitter, could only remain in the telescope's field of view for a very specific amount of time. That time was 72 seconds. You look again at the data. The 6EQUJ5 sequence consists of 6 data points. The computer, as you recall, took one reading every 12 seconds. 6 readings multiplied by 12 seconds gives you a total duration of 72 seconds. The signal was present for the absolute maximum time it possibly could have been. It wasn't a fleeting blip of static lasting a few seconds. It wasn't a long, droning signal that went on for minutes. It appeared precisely as the source entered the beam, and it disappeared precisely as the source left it. This fact is a powerful argument against any earthly origin. Imagine a signal from a high-altitude airplane. It would be moving across the sky at its own speed, on its own path, and would transit the telescope's beam in a much shorter time. The same is true for a satellite in low Earth orbit. A signal from a ground source, perhaps bouncing off a piece of space debris, would be unpredictable, unlikely to produce such a clean, perfectly timed event. But a signal that adheres so perfectly to the 72-second transit window behaves exactly like a source that is fixed to the celestial sphere. It behaves as if it's anchored in deep space, billions of miles away. The intensity profile you deciphered earlier, the perfect bell curve from 6 up to U and back down, reinforces this conclusion. It's the sonic footprint of an object entering the edge of the beam, lower intensity, passing through the center where the telescope's focus is sharpest, peak intensity, and then fading as it exits the other side. The duration and the shape of the signal are in perfect harmony, both screaming the same conclusion. The source is not from around here. Just as this third piece of evidence seems to lock the case into place, you uncover a lesser-known, confounding detail in the telescope's design. It's a frustrating wrinkle, a detail that both deepens the mystery and provides ammunition for skeptics. Dr. John Krauss, in his genius, had equipped the Big Ear not with one receiver horn but with 2. They sat side by side in the focal trench and were affectionately nicknamed Paul and Robert by the staff. They were positioned in such a way that their beams were slightly offset. As the Earth rotated, a celestial source would first pass through the beam of the eastern horn, Paul. It would be observed for 72 seconds. Then there would be a gap of approximately 3 minutes. After that gap, the same object would drift into the beam of the western horn, Robert, and should be detected for another 72 seconds. This 2-horn system was a brilliant, built-in redundancy check. It was designed to eliminate false positives. Any genuine, persistent signal from deep space had to appear twice. First in Paul, then 3 minutes later in Robert. A random burst of terrestrial interference was incredibly unlikely to repeat itself with that exact 3-minute delay. Therefore, the ironclad rule at the observatory was that for a signal to be considered a true candidate for an extraterrestrial source, it had to be seen by both horns. You feel a knot form in your stomach as you anticipate the next question. You frantically search through Jerry Amon's notes and the original data logs. Where is the second detection? The 6EQUJ5 sequence was recorded by one horn. 3 minutes later, when the source should have been squarely in the sights of the second horn, there is nothing. Absolute silence. The data for the second horn is just the normal random background noise. The signal was there, and then it was gone. It never reappeared. This single fact is perhaps the most maddening and enigmatic aspect of the entire event. The signal passed every other test with flying colors: intensity, frequency, duration, bell curve profile, only to fail the final critical test of confirmation. Skeptics have seized on this point for decades. The lack of a second detection, they argue, proves the signal must have been a one-off burst of terrestrial noise, a bizarre fluke that coincidentally mimicked the profile of a celestial signal. But the mystery cuts both ways. If it was an intelligent source, the silence from the second horn could be a clue in itself. What if the transmitter was simply turned off during that 3-minute window? What if the transmission was a deliberately short, 72-second message aimed at us with incredible precision? Or perhaps the source was not fixed, but moving. Or the signal was part of a sweeping beacon, like a cosmic lighthouse, whose beam illuminated our planet for just over a minute, before continuing its slow sweep across the galaxy. This leads you to a challenging and crucial question that hangs over the entire mystery. Could the signal's abrupt end, and its failure to reappear in the second horn, be more than just a reason for dismissal? Could it, in fact, tell us something fundamental about the nature of the transmission itself? We are faced with a paradox. The very feature that makes the signal questionable is also what makes it so uniquely fascinating. It's a perfect signal that is, by its own observatory's definition, flawed. Does this flaw break the case, or does it invite us to imagine a phenomenon even stranger than a simple continuous beacon? You've now grappled with the signal's strength, its frequency, and its duration. Each element is a compelling piece of a puzzle that seems to point away from Earth and out into the cosmos. Now you must consider what may be the most powerful argument for the signal's artificial nature, a characteristic that is incredibly difficult to replicate through any known natural process. You must return to a detail we touched on earlier: the signal's incredible narrowness, its spectral purity. To truly understand this, you have to visualize the radio spectrum not just as a long keyboard, but as a dense, noisy crowd. Natural astrophysical objects, pulsars, quasars, the swirling gas clouds of nebulae, are the loud talkers in this crowd. They generate immense amounts of radio energy, but they are indistinct. Their voices are broad, covering a wide range of frequencies simultaneously. Listening to a quasar is like trying to listen to a person who is shouting every word in every possible pitch at the same time. It's powerful, but it's messy and unfocused. This is what astronomers call a broadband signal. Technology, however, speaks in a completely different way. An artificial radio transmitter, whether it's a local FM station playing music or a deep space probe sending back data from Jupiter, does the opposite. It takes all of its available energy and focuses it into a very specific, very narrow sliver of the spectrum. It speaks in a clear, pure tone. It's not shouting in every pitch, it's singing a single, sustained, perfect note. This is a narrow band signal. The reason for this is efficiency. By concentrating power into a narrow channel, the signal stands out dramatically from the broadband background noise, allowing it to be detected over much greater distances. It is the difference between a floodlight, which illuminates a wide area weakly, and a laser pointer which sends a concentrated beam of light a huge distance. You look again at the 50 columns of data on the Big Ear printout. Each column represents a channel just 10 kHz kHz wide. The entire 50-channel array covers a spectral width of 500 kHz. The WOW signal in all its 6 EQU J5 glory appeared in just one of those columns. The 49 others remained silent. This tells you that the signal was, at most, 10 kHz wide. It was a laser, not a floodlight. In the cosmic crowd, it was the perfect, clear note of a piccolo cutting through the dull roar of 1,000 incoherent conversations. This single fact is a formidable barrier to any natural explanation. There are simply no known, common astrophysical phenomena that generate powerful, transient radio signals confined to a band this narrow. Some exotic objects, like interstellar masers, can create naturally amplified narrowband signals, but they are typically persistent, located in known star-forming regions and have other spectral characteristics that don't match the WOW signal. The universe, for all its violent and energetic processes, doesn't tend to make things that are this spectrally clean. It's a messy place, and its radio signature reflects that. The WOW signal, by contrast, is an oasis of order in a desert of chaos. Here you discover another subtle yet critical technical point. Our measurement is limited by the tools we use. The Big Ear's receivers had a resolution of 10 kHz per channel. This means that while we know the signal was no wider than 10 kHz, it could have been significantly narrower. The 10 kHz channel is like a bucket we use to catch the signal. The signal itself might have been a stream of water only 1 kHz or 100 Hz, or even just a few hertz wide. The signal was unresolved by the instrument. We know it was incredibly narrow, but we don't know how incredibly narrow. This is another echo of the intensity peaking at the software's limit of U. It has yet another characteristic of the signal that appears to have met or exceeded the capabilities of the very machine that detected it. You can now assemble a complete profile of the transmission. It was powerful enough to max out the observatory's intensity scale. It was transmitted at the single most logical frequency for interstellar communication. Its duration perfectly matched the transit time for a deep space object. And it was so spectrally pure that it defies any easy natural explanation, and may have been even purer than the telescope could measure. This leads you to a final, speculative, but intensely logical question. If you were a highly advanced civilization, and your goal was to announce your presence to emerging technological species across the galaxy, how would you design your signal? You would want to make it impossible to ignore and impossible to mistake for a natural event. You would make it powerful. You would place it at a universal landmark frequency like the hydrogen line, and you would make it artificially narrow, a clear sign of technological manipulation. You would, in short, design something that looks almost exactly like the WOW signal. This forces you to consider a new possibility. What if this wasn't an accidental leak of a planetary radar system or a snippet of an ongoing conversation? What if it was a deliberate hello? You are left to wonder. Given that compressing energy into a narrow band is the most efficient way to be detected across the vastness of space, could the WOW signal have been a hailing signal, a galactic dial tone designed with a specific set of physics-based characteristics to be utterly unmistakable to any young civilization just beginning to point its own radio dishes at the sky? Was this a message engineered not with complex information, but with its very structure serving as the message itself? A message that simply says, "We are here, and we know the rules of the game." The red ink on the page seems to glow with a life of its own. The word WOW is no longer just an annotation, it's a declaration. But a declaration to whom? You are with Jerry Amon in the silence of his study, and you can feel the immense weight of the moment. A discovery of this magnitude cannot be kept to oneself. The solitary experience of finding the anomaly must now give way to the collaborative and often brutal process of scientific verification. His first phone call is to Dr. Bob Dixon, the director of the SETI program at the observatory. A few days later, the printout is in the hands of the man whose vision brought the Big Ear into existence, Dr. John Krause. You find yourself in a small, cluttered office at the Perkins Observatory, the scent of old books and hot coffee in the air. The original printout is spread across a large table, the circled 6EQUJ5, now the undisputed center of gravity in the room. Amon, Dixon, and Krause are hunched over it, their faces illuminated by the desk lamp. The atmosphere is not one of giddy celebration. It is tense, electric, with a mixture of profound excitement and deep, ingrained skepticism. These are experienced scientists. They have seen countless false alarms, signals that turned out to be a passing satellite, a faulty amplifier, or even a distant microwave oven. Their immediate instinctual reaction is not to believe, but to doubt. Their mission now is to try and kill the signal, to find the simple, mundane explanation that will make it go away. It could be military, one of them posits. The Cold War is in full swing, and the skies are filled with secret transmissions, spy satellites, and experimental aircraft. They begin the painstaking work of cross-referencing. They check logs of known satellite orbits. None were in the telescope's beam at that specific time, on that specific date. They scour records of known transmitting frequencies used by various government agencies. Nothing matches. The hydrogen line frequency is a protected part of the spectrum, reserved for radio astronomy. Transmitting there is, for the most part, forbidden. What about a harmonic? Another suggests. Perhaps a weaker, Earth-based signal at a lower frequency was somehow multiplied, creating a phantom harmonic signal at 1420 MHz. The math is complex, but they run the calculations. It's a possibility, but a remote one. To create a harmonic that powerful would require an incredibly strong original signal, something that would have almost certainly been detected by other monitoring stations. There are no such reports. You watch as they work through a checklist of possible contaminants. An airplane? Unlikely. Its speed would produce a much shorter signal, and it would almost certainly have been detected in both of the telescope's horns. A ground-based signal reflecting off a piece of space debris? The geometry is wrong. The source is too high in the sky, far from the ecliptic plane where most debris orbits. A glitch in the computer? They examined the data before and after the event. The system was running perfectly. The columns of data on either side of the anomalous one are clean. The machine seems to have been reporting exactly what it heard. During these first few days, you learn a little-known detail about the signal's early life. It is not yet the wow signal. That name, born from Eamon's private spontaneous reaction, has not yet entered the scientific lexicon. Internally, the team refers to it with cold clinical precision. It is the anomaly from August 15, 1977, at right ascension 19:22 men 24s. They are treating it like a piece of evidence at a crime scene, carefully cataloging it, preserving its integrity, refusing to give it a name that would lend it a premature sense of grandeur or authenticity. It is a data point, not yet a discovery. As the hours of scrutiny turn into days, a subtle shift occurs in the room. One by one, the conventional explanations are examined and found wanting. Every attempt to kill the signal fails. It stubbornly refuses to be explained away. The data is just too perfect. The frequency, the duration, the intensity profile, the narrow-band nature. It's a textbook example of what they had hoped to find. A signal that seems precision-engineered to be recognized as artificial. The initial frantic energy of doubt begins to subside, replaced by a quieter, more profound sense of awe. They are beginning to realize that they might not be able to find an earthly explanation because there isn't one. This brings them, and you, to a critical and fascinating crossroads in the scientific process. At what point does an extraordinary anomaly transition from being a probable error to a credible discovery? And who gets to make that call? There is no clear-cut rule. It's a judgment call, a leap of faith backed by data. They have a single, perfect data point that screams extraterrestrial, but it is just that. A single data point. It has not been repeated. It has not been confirmed. You can feel the immense pressure on Krauss and Dixon. To go public with this could invite ridicule from the wider scientific community if it turns out to be a mistake. It could jeopardize their funding and their careers. But to ignore it, to file it away as an unexplained glitch, feels like an abdication of their entire purpose. After intense discussion, they arrive at the only logical scientific conclusion. They cannot prove it is extraterrestrial, but they have also failed to prove that it is terrestrial. The anomaly stands, a defiant ghost in their machine. The only way forward is to try and find it again. The decision is made. They will retrain the big ear on that exact patch of sky in Sagittarius. They will listen, night after night, with every ounce of sensitivity the great telescope possesses. They are going back to the source, hoping to hear that impossible voice a second time. The scramble to debunk has ended. The hunt has begun. The decision has been made. The quiet, methodical sky survey that has been the Big Ear's lifeblood for years is immediately put on hold. The observatory now has a new mission, a singular, obsessive focus. You feel a palpable shift in the atmosphere around the project. The slow, patient work of mapping the sky has been replaced by the urgent, thrilling intensity of a hunt. The target is a tiny, invisible point in the constellation Sagittarius. a point from which the universe, for 72 fleeting seconds, seemed to have spoken directly to them. You are there with the team on the first night of the new search. The air is cool and filled with anticipation. As the Earth turns and brings the target coordinates into view, a profound sense of occasion hangs over the small control room. All eyes are on the equipment. All ears are tuned to the hum of the machines. The teletype printer, usually an object of mundane background noise, is now the oracle. They are no longer just collecting data. They are waiting for a prophecy to repeat itself. The first columns of data from the target region begin to print. Your eyes, along with theirs, scan the fresh ink for any sign of a number higher than a 2 or 3. A5 appears. Hearts leap, adrenaline spikes. But it's gone in the next reading. A momentary flicker of noise, nothing more. A 4 appears in a different channel, another false alarm. The night wears on, a slow procession of ordinary, meaningless numbers. By the time the source drifts out of the telescope's beam, there has been nothing. Disappointment hangs in the air, but it's tempered by resolve. It's only the first night. Night after night, the vigil continues. You become part of the rhythm of the search. You watch the stars rise, you watch the telescope listen, and you watch the paper spool out filled with cosmic silence. The initial feverish excitement inevitably begins to wane, slowly replaced by a stubborn, patient hope. Weeks turn into a month. The team has now scanned the target region dozens of times. They have tried listening on slightly different frequencies just in case the signal had drifted. They have recalibrated their equipment endlessly. The result is always the same. Nothing. The voice is gone. Word of the August 15th detection begins to spread through the hushed circles of the astronomical community. The story of the circled 6EQUJ5 and the WOW annotation becomes an object of intense curiosity and debate. And with this new attention comes new resources. You journey in your mind from the quiet fields of Ohio to the lush, mountainous landscape of Puerto Rico, home to the Arecibo Observatory. Here, nestled in a natural sinkhole, is a telescope of almost unimaginable power. A colossal 1,000-foot, 305-meter fixed dish, the largest and most sensitive radio eye on the planet. If the signal is still broadcasting, even at a fraction of its original strength, Arecibo will hear it. The world's most powerful ear is now being trained on the WOW signal's coordinates. The search has leveled up. You can feel the heightened stakes. A confirmation from Arecibo would be undeniable, a world-changing event. The observations are conducted with meticulous care, but the result is the same. The data comes back clean, not a whisper, not a hint of the galactic shout that the big ear recorded. The silence is now deeper, more profound. It's one thing for the big ear to miss it, but for Arecibo to hear nothing at all is a heavy blow. Other major observatories also take a look. The powerful telescopes of the National Radio Astronomy Observatory in the United States and other instruments around the world are intermittently pointed towards the source. Each search adds another layer to the growing mystery. No one can find it. The signal is a ghost that appeared to one witness on one night and has never been seen again. Back in Ohio, the search continues for years. Whenever there is a gap in the Big Ear's primary survey schedule, they return to the spot. It becomes a kind of pilgrimage, a return to a sacred place in the sky, but the source remains stubbornly, maddeningly silent. The frustration among the team is palpable. They hold in their hands a piece of paper that could be the most important artifact in human history, but they are completely unable to find any corroborating evidence. The signal becomes a legend, an observatory ghost story, a tale of the one that got away. You are left to contemplate the outcome of this great hunt. The frantic search has wound down, replaced by a long, slow acceptance of the situation. The signal was a one-time event. This realization fundamentally changes the nature of the mystery. You are forced to confront a deeply unsettling question. What is more profound? A single, inexplicable signal that suggests we are not alone, or the absolute deafening silence that follows it, suggesting that we are? The first offers a tantalizing, explosive possibility. The second is a cold, empty void, a question mark that echoes into infinity. The Great Silence is, in its own way, more mysterious and more terrifying than the signal itself. It implies that we may have overheard a whisper from someone who is now gone, or from a beacon that has since turned its gaze to another distant star, leaving us alone again in the darkness, wondering if what we heard was real at all. The silence from Sagittarius is deafening. In the years following the event, the lack of a second signal creates a vacuum, and that vacuum is quickly filled with doubt. The initial excitement has faded, and the cold light of scientific scrutiny intensifies. If the signal won't show itself again, then perhaps the original data was flawed. Perhaps there is a simple, mundane explanation that was overlooked in the initial rush. You find yourself compelled to play the skeptic, to put on the detective's hat, and rigorously re-examine every possible terrestrial suspect, no matter how unlikely. Your first suspect is a familiar one, an aircraft or an artificial satellite. It's the most common source of false alarms in radio astronomy. You pull up the flight logs and satellite tracking data for the night of August 15, 1977. As the original team discovered, there were no known satellites or aircraft in the Big Ear OIS beam at the moment of detection. But you press deeper. What if it was an unlogged clandestine flight? Even so, the evidence in the signal itself argues against it. An object moving at high speed through the atmosphere or in low Earth orbit would transit the telescope's narrow beam in a matter of seconds, not the 72 seconds that were observed. Furthermore, its signal would be subject to a significant Doppler shift. The frequency would appear to rise as it approached and fall as it moved away, like the changing pitch of a police siren. The WOW signal was remarkably stable, its frequency locked in place. Suspect number 1 is dismissed. Next, you turn to a more tantalizing possibility: a secret military experiment. Could the signal have been a new type of communication or radar technology, beamed from a hidden transmitter or a spy satellite in a high orbit? This theory has the appeal of explaining the signal's power and artificial nature. However, the choice of frequency makes it highly suspect. The 1420 to 1427 MHz band is a globally protected quiet zone for radio astronomy, established by international treaty. For a government to conduct a powerful secret test in the one slice of the spectrum that the world's astronomers are watching most intently seems not just careless, but counterintuitive. It's like testing a top-secret submarine in the middle of a naval parade. While you can't rule out the possibility of such a reckless breach of protocol, it stretches credulity. This is where the investigation gets more complex, leading you to a more obscure but seriously considered hypothesis. Could the signal have originated on the ground, hundreds or even thousands of miles away, and bounced off something in orbit? You are now investigating the space debris reflection theory. Imagine this scenario. A powerful, narrow-band radio transmitter somewhere on Earth is operating, perhaps illicitly. Its signal travels up into space and strikes a piece of orbital junk, a discarded rocket stage, a defunct satellite, even a lost tool from an Apollo mission. This piece of debris, acting as an accidental mirror, reflects the signal downwards, where it is intercepted by the Big Ear. On the surface, this seems plausible. It would explain why the signal was never heard again. The unique alignment of transmitter, reflector, and receiver would be a fleeting, one-time event. But as you dig into the specifics, you realize the chain of coincidences required is staggering. First, the ground transmitter would need to be exceptionally powerful and transmitting on a protected frequency. Second, the piece of space junk would have to be in the precise location in space to create the reflection. Third, it would need to have a flat metallic surface of the right size to act as an efficient mirror. Fourth, and most critically, this tumbling piece of junk would have to be moving at the exact speed and trajectory to remain in the Big Ear's beam for a full 72 seconds, perfectly mimicking the transit of a fixed celestial object. It would have to be a geosynchronous piece of junk in a part of the sky where such objects are rare. You are no longer talking about a simple reflection. You are talking about a cosmic bank shot of unbelievable complexity and unlikelihood. The odds of all those variables lining up perfectly at the same moment are astronomically low. It is a theory that is possible, but profoundly, deeply improbable. You have now systematically interrogated the prime mundane suspects. Each one has an alibi or a story so full of holes and improbable coincidences that it falls apart under pressure. You are left at an intellectual impasse, a place that scientists often find uncomfortable. You have a phenomenon that is real. The data on the page is undeniable, but it resists every conventional Earth-based explanation you can construct. This forces you to confront a philosophical question about the nature of truth and evidence, a question often framed by the principle of Occam's razor, which states that the simplest explanation is usually the correct one. But what is the simplest explanation here? Is it the terrestrial explanation, which requires a long, convoluted chain of extreme improbabilities, a veritable cascade of cosmic coincidences? Or is the simpler explanation the extraordinary one, that the signal came from a non-human technological source in deep space? It is a genuine paradox, so you must ask yourself, how much improbability are we willing to accept in a mundane explanation before an extraordinary one becomes the more logical, if not simpler, conclusion? It is a line in the sand, and you, and the entire scientific community, are left standing right on top of it. You have methodically cleared the scene of all terrestrial suspects. The alibis are too strong. The required coincidence is too astronomical. Your investigation must now leave the confines of Earth's atmosphere and venture into the vast wilderness of the cosmos itself. You must now consider a different class of culprits. Not intelligent aliens, but natural ghosts in the machine. Are there known astrophysical phenomena, born from the chaos of stellar physics, that could have created a phantom signal, a perfect mimic of an artificial broadcast? Your first cosmic suspect is a pulsar. These are the rapidly spinning, hyper-dense corpses of massive stars. As they rotate, they sweep beams of intense radio waves through space like a cosmic lighthouse. If this beam happens to sweep across Earth, we detect it as a regular repeating pulse. Could the WOW signal have been a previously unknown pulsar? You examine the evidence. The power is certainly there. Pulsars are energetic enough, but the signature is all wrong. The WOW signal was a single sustained 72-second event, not a series of rapid pulses. More importantly, like almost all natural radio sources, pulsars are broadband emitters. Their energy is spread across a wide range of frequencies. The WOW signal was a pure, narrowband tone. The pulsar theory doesn't hold up. Next, you consider a quasar or a flaring star. A quasar is the incredibly bright active nucleus of a distant galaxy, one of the most luminous objects in the universe. A flaring star is a more local phenomenon, a star that undergoes a sudden violent eruption of energy from its surface. Could the signal have been an extreme, once-in-a-billion-year flare from a faint, undiscovered star that just happened to be in the Big Ear's beam? This could potentially explain the signal's transient nature. It was there, and then it was gone. But you once again run into the brick wall of bandwidth. Flares and quasars are products of chaotic thermal processes. They are the definition of broadband noise. They simply do not produce the clean, spectrally pure note that defines the WOW signal. The alibi is solid. The investigation seems to be stalling. The usual suspects of the radio universe don't fit the profile. But then you uncover a more subtle, more elegant, natural explanation. It's a phenomenon known as interstellar scintillation. You are already familiar with its effects. When you look up at the night sky, stars appear to twinkle. This twinkling isn't caused by the stars themselves. It is the result of their light being distorted as it passes through the turbulent layers of Earth's atmosphere. The same thing happens in deep space. The empty space between stars is not truly empty. It's filled with a thin, clumpy soup of charged particles and plasma. When radio waves from a very distant source, like a quasar, travel through this interstellar medium for thousands of light years, they get bent and distorted. Occasionally, clumps of this plasma can act like a cosmic lens, focusing the faint, distant radio waves and causing them to flare up in intensity for a brief period. This is interstellar scintillation. You lean forward, intrigued. This theory seems to have real promise. It could explain why the signal was so powerful. A weak background source was momentarily magnified. It could explain why it was so transient. The specific alignment of the source, the plasma lens, and Earth was fleeting. And it could explain why it has never been seen again. That exact alignment is unlikely to ever recur. It's a natural, albeit rare, event that could account for many of the signal's bizarre properties. For a moment, you think you might have found your ghost, but then You remember the signal's most defining characteristic. You ask the critical question, what does scintillation do to the bandwidth of a signal? The answer is the theory's fatal flaw. A lens, whether it's made of glass or interstellar plasma, can only focus the light that passes through it. It cannot change the nature of that light. If you use a magnifying glass to focus the light from a frosted broadband light bulb, you get a brighter, more intense spot of frosted broadband light. You do not get a laser beam. Interstellar scintillation would have taken the faint broadband signal from a distant quasar and made it into a strong broadband signal. It cannot explain the wow signal's incredible, laser-like narrowness. With that single damning fact, the most sophisticated natural explanation on the table dissolves. You are now in a profound and deeply unsettling place. You have exhausted the list of conventional suspects both on Earth and in the heavens. Every attempt to categorize the wow signal, to place it within the known taxonomy of the universe, has failed. It doesn't look like a human-made signal. It doesn't look like any known pulsar, quasar, or stellar flare. And it doesn't fit the profile of a rare event like interstellar scintillation. It is a true anomaly, a piece of data that fits in no existing box. This forces you to ask a question that pushes at the very boundaries of scientific inquiry. If the signal wasn't from Earth and it doesn't match any known natural phenomenon governed by the laws of physics as we currently understand them, are we forced to consider it a supernatural event? Not in the sense of ghosts or magic, but in the most literal meaning of the word. A phenomenon that is, for now, supernatura, above or beyond our current model of the natural world. Are we dealing with a new, undiscovered type of astrophysical object with properties we can't yet imagine? Or does the stubborn refusal of the signal to fit our laws of nature suggest it was created by something that can manipulate those laws? Technology? The years have folded into decades. The printout with its red-inked wow is now a historical artifact. The Big Ear telescope itself is gone, dismantled to make way for a golf course. The case has gone cold, graduating from an active investigation into the realm of scientific folklore. You've exhausted all the conventional suspects from the 1970s, both terrestrial and celestial, and have been left on the unnerving precipice of the truly unknown. The silence from Sagittarius has become a permanent fixture in the astronomical landscape. Then, 40 years after the event, the silence is broken. Not by a new signal from the stars, but by a new voice here on Earth. The year is 2017. A new investigator, Professor Antonio Paris of St. Petersburg College in Florida, steps forward with a startlingly elegant and radically simple hypothesis. He proposes a new suspect, one that has been hiding in plain sight the entire time. He suggests that the source of the wow signal was not an alien transmitter but a comet. You find yourself in a new era of astronomy, one of computers and vast digital archives. Paris and his team dive into astronomical databases, searching for any known objects that might have been in the Big Ear's field of view on that specific night. They are looking for ghosts in the historical data, and they find two comets designated 266PO Christensen and P2008Y2 Gibbs were not discovered until the 21st century. But by calculating their orbits backward in time, Paris argues that on August 15, 1977, they were transiting the very patch of sky in Sagittarius that the Big Ear was observing. The hypothesis is captivating in its simplicity. You picture a comet, a dirty snowball of ice and rock making its journey through the inner solar system. As it gets closer to the sun, the solar radiation heats its surface, causing the ice to sublimate directly into gas. This process releases a vast, tenuous cloud of material around the comet's nucleus, a cloud called a coma. This coma can stretch for millions of miles, and it is composed largely of water vapor, which is quickly broken down by sunlight into its constituent atoms, hydrogen and oxygen. Suddenly, all the pieces seem to click into place. A comet, you realize, is surrounded by an enormous invisible cloud of neutral hydrogen. And what does a cloud of neutral hydrogen do? It naturally emits radio waves at a very specific frequency, 1420 MHz, the hydrogen line. You can feel the appeal of this theory, the way it seems to neatly solve so many of the signal's most vexing puzzles. The frequency? Explained. It's the natural emission of the comet's hydrogen cloud. The fact it was never heard again? Explained. Comets are moving targets. By the time Krauss and his team looked for the signal again, even just a day later, the comet would have moved far away from that specific point in the sky. They were staring at an empty spot where a comet used to be. The location in Sagittarius. Explained. The orbital mechanics, according to Paris, put his cometary suspects at the scene of the crime. Even the confounding single horn detection could potentially be explained. Perhaps the hydrogen coma was not uniform, but clumpy, and a particularly dense clump of gas happened to drift through one of the telescope's beams but missed the other. It feels like a breakthrough. The theory spreads like wildfire through the media. Headlines around the world declare the 40-year-old mystery solved. The alien signal, the great enigma, was nothing more than the whisper of a passing space rock. It's a mundane answer, perhaps a disappointing one, but it has the satisfying ring of scientific closure. But Professor Paris doesn't just stop at the hypothesis. He attempts to provide experimental proof. Here, you discover a lesser-known aspect of this modern chapter of the story. To test his idea, Paris and his team acquired time on a 10-meter radio telescope. They waited until January 2017, when one of the suspect comets, 2666P per Christensen, once again passed through the same region of the sky the Big Ear had been watching. They pointed their telescope at the comet and listened, and according to their published paper, they detected a signal at 14 or 20 MHz. The signal was weak, but it was there. They claimed to have successfully observed the hydrogen emission from the comet, providing a proof of concept for their theory. It seemed to be the smoking gun. You are left to ponder this elegant, seemingly complete solution. It feels so neat, so tidy, yet it exists in a strange state of limbo. The original event is now a distant memory, an observation captured on aging paper by a machine that no longer exists. The proposed culprit is a comet that no one even knew existed at the time. The proof is a modern experiment conducted with a different instrument under entirely different conditions. This raises a profound and difficult question about the nature of solving historical mysteries. How does the inexorable passage of time affect our ability to find the truth? We can never go back to that August night in 1977. We can never perfectly replicate the atmospheric conditions, the exact state of the Big Ear's electronics, or the true position and outgassing rate of a comet whose existence was then unknown. So can a hypothesis like this ever be truly proven, or for that matter, disproven? When the original crime scene is gone forever, we are left to weigh the plausibility of stories, and you must wonder if this compelling new tale is the final chapter, or just another ghost in the machine. The comet theory hangs in the air, gleaming with the appeal of a perfect solution. It feels right. It feels rational. It takes a wild, romantic story about a call from the stars and grounds it in the familiar, predictable physics of our own solar system. For a moment, you let yourself believe that the case is finally closed, the ghost finally laid to rest. But in science, a headline is not a conclusion, and a compelling story is not a substitute for rigorous proof. The ink was barely dry on the 2017 paper when the scientific community began to push back, and you find yourself now in the middle of a fierce debate. You are no longer just an observer, you are part of the peer review process. You must listen to the voices of other radio astronomers, including some who were part of the original Big Ear team, as they dissect the comet hypothesis. Their critique is not personal, it is a clinical, evidence-based dismantling of what they see as a deeply flawed explanation. The first and most devastating counterargument is about the signal's strength. You recall the sheer power of the WOW signal, peaking at an intensity more than 30 times the background noise. This is where you encounter a crucial, lesser-known detail that challenges the very foundation of the comet theory. Yes, comets are surrounded by hydrogen clouds, and yes, those clouds emit radio waves at 1420 MHz. However, this emission is incredibly faint. The hydrogen gas in a comet's coma is extraordinarily diffuse, with a density far lower than the best vacuums we can create in a lab on Earth. According to calculations by other astronomers, for a comet to generate a signal strong enough for the Big Ear to detect at an SNR of 30, it would need to be releasing an impossibly, absurdly large amount of hydrogen. It would have to be an unprecedented supercomet shedding material at a rate thousands of times greater than any comet ever observed, like Halley's Comet or Hale-Bopp. The two comets proposed by Paris, 266P Christensen and P 2008Y2 Gibbs, are small, faint, and unremarkable. There is simply no physical mechanism that could explain how such ordinary comets could produce such an extraordinary shout. It's like claiming a flickering candle produced a searchlight beam. The numbers just don't add up. The second critique attacks the signal's spectral purity. You remember the narrow-band nature of the signal. It was a pure tone, less than 10 kHz wide. Natural hydrogen emission, however, is subject to thermal broadening. The hydrogen atoms in the comet's coma are not stationary. They are buzzing around randomly. This motion causes a Doppler effect, smearing the signal out across a wider band of frequencies. A signal from a comet's hydrogen cloud should be broadband, not narrowband. This directly contradicts one of the WOW signal's most distinctly artificial-looking characteristics. In fact, the signal that Paris himself detected from Comet 266P in his 2017 experiment was broadband, which critics point out serves as evidence against his own theory, not for it. Third, you must re-examine the smoking gun experiment. Paris's detection of a 1420 MHz signal from the direction of a comet seemed at first like definitive proof, but other radio astronomers were quick to offer a much simpler explanation. The region of the sky where the signal originated, Sagittarius, is located in the dense plane of our own Milky Way galaxy. This region is filled with vast diffuse clouds of interstellar hydrogen, all of which naturally glow at 1420 MHz. Critics argue that when Paris pointed his small telescope in that direction, he wasn't seeing the comet at all. He was simply seeing the ever-present background hum of our own galaxy. It's a classic signal versus noise problem, and in this case the galactic noise is a far more likely source for his detection than the faint comet. Finally, even the premise that the comets were in the right place at the right time is called into question. Independent researchers reran the orbital calculations and concluded that neither of the two comets was actually within the Big Ear's beam at the time of the detection. The proposed culprits, it seems, don't even have a solid alibi for being at the scene of the crime. One by one, the pillars of the comet theory begin to crumble under the weight of scientific scrutiny. The elegant, simple solution reveals itself to be anything but. You are left with a powerful and frustrating disconnect. The media ran with the exciting mystery-solved story, and for many that became the final word. The subsequent refutations, technical, nuanced, and published in scientific journals, received almost no mainstream attention. This forces you to confront a challenging question about the gap between public perception and scientific reality. How does the public's understanding of a scientific mystery, often shaped by sensational headlines, and a desire for neat conclusions diverge from the rigorous, messy, and often much slower process of building a scientific consensus? The comet theory was a compelling story that offered closure. The scientific pushback, while more accurate, offers only a return to the original unsettling mystery. It seems the public would rather have a tidy, incorrect answer than live with a magnificent, unresolved question. And so, the ghost of the WOW signal, briefly thought to be exorcised, returns to its haunt, leaving the mystery deeper and more resilient than ever. The comet theory has been weighed, measured, and found wanting. The terrestrial suspects have been cleared. The known celestial culprits have solid alibis. The investigation has come full circle, leaving you once again with the pristine, unexplained data on that 40-year-old printout. You have exhausted the how and the what. Now you find yourself drawn to the where. You must journey to the scene of the crime itself, not as it is now, but as it was on that August night in 1977. Your destination is a specific anonymous point on the celestial map, located in the constellation Sagittarius. You leave the Earth behind, your perspective shifting from a single observatory in Ohio to a traveler's view of the galaxy. You set your course for the southern sky, towards the familiar teapot-shaped asterism that marks the Archer, Sagittarius. But as you travel, you realize this is no ordinary constellation. This is a special direction. Looking towards Sagittarius is like standing on the outskirts of a vast, sprawling city, and looking downtown towards the glittering, light-drenched city center. For in this direction lies the heart of our own Milky Way galaxy. The view becomes more and more spectacular. The sparse stars of our local neighborhood give way to an immense, luminous haze. You are approaching the galactic bulge, a dense, tightly packed sphere of hundreds of billions of stars, all swirling around the supermassive black hole that marks the galaxy's core. The sky here is not black and dotted with lights. It is a solid, shimmering wall of ancient golden suns. Dark, intricate lanes of interstellar dust, the raw material for future stars and planets, thread through the brilliance, obscuring the view and adding to the profound sense of mystery. This is the oldest, busiest, and most dynamic part of our galaxy. If civilizations are common, this is where you would expect to find the most ancient and advanced among them. You navigate to the precise coordinates recorded by the Big Ear. You are in the northwestern region of Sagittarius, and you find yourself near a breathtaking object, a globular cluster known as Messier 55 or M55. It's a celestial beehive, a dense spherical swarm of 100,000 ancient stars, all locked in a tight gravitational embrace. These are some of the oldest stars in the galaxy, born more than 12 billion years ago. You pause to consider the implications. Could the signal have originated from a planet orbiting one of these primordial suns? A civilization that might have been old when our own solar system was just beginning to form? The thought is staggering. The WOW signal did not come from within M55 itself, but from a patch of sky just to its east. And here, as you zoom in on the specific location, you encounter the immense, frustrating challenge that has faced every astronomer who has tried to identify the source. This is where you come face to face with a lesser-known, but critically important aspect of the search. The problem is one of overwhelming numbers. When modern telescopes are pointed at the precise coordinates of the WOW signal, they don't see an empty patch of space with one or two obvious sun-like stars. They see a blizzard of stars. Thousands upon thousands of them, of every size and color, are packed into the field of view. The region is so dense that it becomes a cosmic needle in a haystack, problem of the highest order. Which one of these countless points of light could be the home of the intelligence that sent the signal? Is it the bright yellow one, the faint red dwarf, or one of the thousands of stars whose light is completely blocked from our view by the thick curtains of galactic dust? The sheer density of the star field makes a follow-up search almost impossible. To investigate each star individually for signs of planets and then to analyze the atmospheres of those planets for biosignatures is a task that would take centuries with our current technology. The signal has given us a precise direction, but that direction points to an impossibly crowded room, leaving us with no way to identify the speaker. The glare from Sagittarius is simply too bright, the crowd of potential sources too vast. This brings you to a deep and fascinating philosophical question. The signal originated from the galactic core, a region that is, in theory, galactic prime real estate. It's where the concentration of heavy elements, the building blocks of planets and life, is highest. The stars are older, giving life more time to evolve and develop intelligence. On one hand, this seems to bolster the extraterrestrial hypothesis. Of course, the first powerful signal we detect would come from the most likely place for advanced life to exist. It's a satisfying, logical fit. But on the other hand, could this be a form of confirmation bias? The galactic center is not just crowded with stars. It is also the most energetic and chaotic region of the galaxy. It is a cosmic laboratory where extreme physics, high-energy phenomena, and exotic objects are the norm. Does the signal's origin near this chaotic core support the idea of an ancient intelligence, or does it actually detract from it, suggesting instead that we may have witnessed a rare, powerful, but entirely natural phenomenon that can only occur in such an extreme environment, a ghost in the machine, that we have yet to identify simply because we have never looked at a place so strange? You are left floating in the stellar glare, wondering if the location is the ultimate clue or the ultimate red herring. You are adrift in the star fields of Sagittarius, overwhelmed by the sheer scale of the place, the impossible number of potential sources. The journey has led you to a dead end. But perhaps you have been asking the wrong question. You have been fixated on the signal's origin and its characteristics, but you haven't truly grappled with its most profound and frustrating feature, its silence. Why would anyone or anything shout into the void with such power and precision only to never speak again? This question has always been the primary weapon in the skeptic's arsenal. A genuine attempt at contact, they argue, would be persistent. It would be a repeating signal, a continuous beacon, something you could lock onto and study. The singularity of the wow signal makes it seem like a fluke, a ghost. But you must now force yourself to turn that logic on its head. What if the silence isn't a flaw in the theory? What if the silence is the point? You must now consider a speculative but compelling idea known as the one-shot beacon hypothesis. To do this, you have to try and think on a truly galactic timescale, from the perspective of a civilization far older and more advanced than our own. Imagine you are part of a species that arose in the dense, ancient star clusters of the galactic core, a civilization that has existed for millions of years. You have explored your corner of the galaxy, and you know that the universe is vast and mostly empty. You suspect, however, that life may be common, but that intelligent, technological life is rare and fleeting. You feel a sense of duty, perhaps, or a desire for cosmic connection. You want to let the younger, emerging civilizations of the galaxy know that they are not the first. You want to build a monument not of stone but of energy, a testament to your existence. What is the most logical and efficient way to do this? Your first thought might be to build a massive, continuous beacon, broadcasting in all directions. But you quickly realize the energy requirements are astronomical. To power such a beacon for the millions of years it might take for a signal to reach a developing species, and for them to evolve the technology to detect it, would consume the energy of entire stars. It is profoundly wasteful. Your second thought might be to send targeted messages to specific, promising-looking stars. But how do you choose? The galaxy has 400 billion stars. The odds of picking the right one at the right time are slim. You would waste immense resources sending messages to dead worlds. This is where the logic of the one-shot beacon comes in. You engineer a third option. You build the most powerful transmitter imaginable. You aim it not at a single star, but at a vast, star-rich sector of the galaxy. Then you pour an immense amount of energy into it for a very short period of time, creating a single brilliant pulse, a flash of artificiality designed to be unmistakable. This pulse has all the characteristics needed to get noticed. It's incredibly powerful. It's on a universally significant frequency like the hydrogen line, and it's spectrally pure. And then once the pulse is sent, you turn the transmitter off. You have made your statement. You have planted your seed. You have sent your 72-second postcard from the void. You may then re-aim your transmitter at a different sector of the galaxy and repeat the process. Over 1,000 years you might send out 1 million such pulses, but for any single star system, it would be a singular, unrepeated event. Here you realize you are tapping into a core concept within the SETI community. Researchers like the venerable Dr. Jill Tarter have long made a distinction between different types of potential alien signals. There could be targeted messages, full of rich data, aimed directly at us. But it's perhaps more likely we would first detect a hailing signal, a simple, powerful broadcast designed merely to attract attention, like a cosmic dial tone. The wow signal, with its lack of any discernible encoded information, perfectly fits the profile of a hailing signal. Its structure is the message. The message is simply, someone with technology is here and this is the channel we are using. The one-shot beacon hypothesis elegantly resolves all the major paradoxes of the wow signal. Its power is explained by the need to be seen across the galaxy. Its artificial characteristics are explained as deliberate design features to distinguish it from nature. And most importantly, its singularity is explained not as a flaw, but as a deliberate, energy-efficient strategy. The signal wasn't the start of a conversation. It was an announcement. This forces you to reevaluate everything, to ask a truly challenging question that inverts the entire problem. For 40 years we have asked, if it was aliens, why didn't they repeat the signal? Now you must ask, if an advanced civilization wanted to announce its existence to the galaxy, would a single, powerful, unrepeated beacon be a more logical and energy-efficient strategy than maintaining a continuous broadcast for thousands of years? Suddenly, the signal's strangest feature becomes its most logical. The silence is no longer evidence against intelligence. The silence is perhaps the ultimate proof of it. It speaks of a mind that is patient, efficient, and thinks on a timescale that we can barely comprehend. You have accepted the logic of the one-shot beacon. It is a compelling, elegant, and chillingly patient strategy for making one's presence known across the galaxy. The signal's purpose in this view was simply to be an unmistakable sign of technology, a cosmic "we were here." But as you continue to stare at the 6 characters, 6EQUJ5, a new, more tantalizing possibility begins to emerge. What if the signal was more than just a hailing call? What if the message wasn't just that it was, but in what it was? You must now venture into the speculative fringe to entertain the idea that there is a deeper message encoded in the mathematics of the signal itself. You begin by looking at the known facts. The intensity of the signal rose and fell in a near-perfect bell curve, which is exactly what you'd expect from a fixed source transiting the telescope's beam. The sequence of measured signal-to-noise ratios, roughly 6, 14, 26, 30, 19, 5, has always been interpreted as a simple reading of this effect. The source gets louder as it moves to the center of the beam, then quieter as it moves away. This is the standard, accepted interpretation. But you must now challenge that assumption. Imagine the intelligence behind the signal. If they are capable of building a transmitter of such power, they are masters of physics and engineering. They would almost certainly be able to model the basic properties of a simple radio telescope like the Big Ear. They would know that their signal would be perceived as a rising and falling bell curve. What if they used this knowledge? What if they deliberately modulated their signal's power, piggybacking a message onto the natural shape of the transit? What if the numbers 6, 14, 26, 30, 19, and 5 are not just passive measurements, but deliberate chosen values? You have now stepped into the world of cosmic cryptology. For decades, a small community of independent researchers, amateur astronomers, and curious mathematicians have attempted to do just this, to find a pattern, a hidden meaning, in that short string of numbers. You delve into their work, a fascinating collection of intricate theories and mind-bending calculations. Some have tried to link the numbers to the atomic weights of fundamental elements. Is there a message in the chemistry of life? Others have looked for relationships with prime numbers, the universal language of mathematics. Could the sequence be the beginning of a mathematical primer, a simple statement of universal truth? This is where you uncover a lesser-known, truly fringe line of inquiry. Some have looked beyond the intensity and focused on the frequency itself. The signal was detected at 1420, 4556 MHz. The true rest frequency of neutral hydrogen is 1420, 405575 MHz. There is a small but significant offset. Why? Perhaps it was a Doppler shift from the source's movement. Or as these fringe theories propose, perhaps the offset itself is part of the message. One researcher, for example, pointed out that the mathematical constant pi-1 multiplied by the hydrogen line frequency yields a number very close to the one detected. Is this a coincidence? Or is it a deliberate signpost, a way of saying, we not only know about hydrogen, we also know about the fundamental geometry of a circle? You follow these threads not as a believer, but as an open-minded investigator. You see attempts to graphically plot the intensity values, looking for a recognizable shape. You see analyses that convert the alphanumeric characters to binary, searching for a hidden bit stream of data. None of these theories have gained any traction in the mainstream scientific community, and for good reason. They are unfalsifiable. There are infinite mathematical patterns one can search for in any small set of numbers, and with enough effort, you are bound to find something that looks significant. This leads you to a crucial and challenging psychological question. Are you witnessing a brilliant act of decryption, or are you simply watching a profound act of pareidolia? Pareidolia is the human tendency to perceive meaningful patterns in random or ambiguous data. Seeing a face in the clouds, a man in the moon, or hearing hidden messages in a song played backward. Our brains are hardwired to be pattern recognition machines. It is a survival trait, but this powerful instinct can also lead us astray, causing us to impose meaning where none exists. Is the hunt for a message in the numbers of 6EQUJ5 the ultimate act of cosmic pareidolia? Are we so desperate for the universe to speak to us in a language we understand, the language of mathematics, that we are willing to see a complex message in what is most likely a simple series of signal strength measurements? Or, on the other hand, are we being too dismissive? Could a truly alien intelligence choose to communicate in this very way, using a meta-message encoded in the physical properties of the signal itself? To reject the possibility out of hand might be a failure of imagination, a form of intellectual chauvinism that assumes any message must look like our own. You are caught between two powerful impulses: the scientist's demand for rigorous, verifiable evidence, and the explorer's hope for profound, hidden meaning. Are we guilty of seeing patterns in the static, or are we failing to recognize a form of communication so subtle and advanced that it is simply beyond our current paradigms of thought? You have journeyed to the galactic core, you have delved into the fringe mathematics of alien communication, and you have wrestled with theories of cosmic beacons. Now, you must return to Earth, to that quiet study in Ohio, and to the man whose life became inextricably woven into the fabric of this mystery. The signal is not just a collection of data, it is a human story, and at its heart is the quiet, thoughtful volunteer who was the first to see the anomaly. You must now consider the life of Dr. Jerry R. Amen after he wrote "Wow." In the wake of his discovery, you might imagine a life transformed into one of celebrity and spectacle. You can picture the television interviews, the book deals, the lecture circuits. But that is not what happened. You discover that Jerry Amen was a man defined not by the sensationalism of his finding, but by a deep, unwavering commitment to the quiet, humble process of science. He remained a professor, a dedicated teacher, and a meticulous researcher. The man who found the most compelling evidence for extraterrestrial intelligence in history never became a public advocate for the existence of aliens. You watch him over the years as he is inevitably drawn into the public discourse about the signal. In every interview, in every article, his tone is one of remarkable caution and intellectual honesty. He becomes the world's foremost expert on the event, and he uses that platform not to promote a belief, but to present the data, warts and all. He would meticulously lay out the arguments for why the signal looked artificial, its intensity, its frequency, its narrow band nature. Then, just as meticulously, he would present the arguments against it. The crucial fact that it was only detected in one of the telescope's two horns and the profound unending silence that followed. He refused to make the leap of faith. His position was always the same. It was the most interesting signal he had ever seen, but it remained a mystery, not a confirmation. As the decades pass and the silence from Sagittarius continues, you begin to see a subtle but profound shift in his thinking. Here you discover a lesser-known and poignant detail about the man who saw "Wow." The initial electrifying awe of that moment in his study slowly gave way to a long, sober reflection on the nature of probability. He saw his colleagues and the world's most powerful telescopes stare at that patch of sky for years and find nothing. The sheer improbability of a single 72-second alien broadcast that never repeated began to weigh on him. In his later years, he wrote about his evolving perspective. He stated that while the extraterrestrial hypothesis could not be completely ruled out, he had come to believe that a terrestrial source was, in the end, the more likely explanation. He revisited the very theory that seemed so improbable at first, the idea of a signal from Earth bouncing off a piece of space debris. He acknowledged the chain of coincidences required for this to happen was mind-boggling. But as a scientist dealing in statistics, he began to wonder if a 1 in a trillion chance of a bizarre terrestrial reflection was perhaps still more probable than a 1 in a trillion chance of a genuine ETI signal. It is a startling admission. The man who gave the signal its name, the human face of this cosmic mystery, eventually became one of its most rigorous and public skeptics. This was not a retraction of his discovery, but the final, beautiful act of a scientific mind, following the evidence, or lack thereof, to its most logical, if least romantic, conclusion. This journey from unfiltered awe to profound doubt forces you to consider the immense personal burden that comes with such a discovery. You try to put yourself in his shoes. What is the personal and psychological burden of being the sole, primary witness to a potentially history-altering event that can never be replicated? Your name is forever attached to a ghost. For the rest of your life, people will ask you with hope in their eyes, was it them? And for the rest of your life, the only honest answer you can give is, I don't know. You are the keeper of a sacred relic that might be a holy grail or might be a meaningless piece of noise. You carry the weight of that ambiguity. Jerry Amon passed away in 2020, his name forever etched alongside the mystery he uncovered. He left behind a legacy of integrity and caution. He gave us the wow, but he also gave us the what if. His life serves as a powerful reminder that science is not about finding the answers we want, but about honestly grappling with the data we have, no matter how incomplete or maddeningly inconclusive it may be. Your focus now shifts from the man to the machine. You return to that field in Delaware, Ohio, but it is no longer 1977. 2 decades have passed. The world has changed. The Cold War that spurred the Big Ear's creation is over. The technology of radio astronomy has marched on, leaving the elegant but aging Krauss-type telescope behind. Newer, more powerful, and more agile instruments now dominate the scientific landscape. The Big Ear, the silent giant that once overheard a whisper from the void, is now seen by many as a relic, a living fossil from a bygone era. You can feel the encroaching presence of the modern world. The quiet, isolated farmland that was once the perfect location for a sensitive radio observatory is no longer so quiet. The nearby city has grown, its suburbs pushing outwards, bringing with them the very radio noise and light pollution the observatory was built to escape. The land upon which the great telescope stands has become valuable real estate. A new kind of pressure is mounting, one that has nothing to do with budgets for science or the search for extraterrestrial life. It's the pressure of property values and urban development. In 1997, the news becomes official. The Ohio State University, which owns the land, has sold it to a commercial real estate developer. The plan is to expand the neighboring golf course and build a community of luxury homes. The fate of the Ohio State University Radio Observatory is sealed. After 36 years of service, its vigil will come to an end. The Big Ear is scheduled for demolition. As the news spreads, you witness a new chapter in the telescope's story. A passionate, desperate fight to save it. Here you discover a lesser-known detail, a final, defiant stand made by those who understood the instrument's true worth. A coalition of scientists, engineers, former volunteers, and space enthusiasts launches a campaign. They argue that the Big Ear is more than just an obsolete piece of equipment. It is a historical landmark. It is a monument to the ingenuity of post-war American science. And more than that, it is the site of an event that could one day be recognized as a turning point in human history. They petitioned to have it designated as a National Historic Landmark, a status that would protect it from the bulldozers. They try to raise funds, hoping to buy the land back or even to finance the monumental task of moving the colossal structure to a new home. You can feel the passion and the urgency of their efforts. For them, destroying the Big Ear is not just scrapping metal. It is an act of cultural vandalism, like tearing down a pyramid or flooding a sacred cave. It is the place where humanity may have been spoken to, and to erase it from the landscape seems like an act of profound disrespect to the mystery it represents. But their campaign, heartfelt as it is, ultimately fails. The forces of commerce and perceived progress are too strong. The designation is denied. The funds cannot be raised. The appeal is lost. You find yourself there in 1998, a silent witness to the end. You watch as the demolition crews arrive. The process is methodical, efficient, and utterly heartbreaking. You see the vast 700-foot parabolic reflector, which once focused the faint whispers of the cosmos, torn apart by heavy machinery, its precisely curved panels bent and mangled. You watch as the tiltable flat reflector, which for decades stood like a great sail against the sky, is felled. The wire mesh which formed the delicate listening surface of the ear is ripped down and hauled away for scrap. The concrete trench that housed the sensitive receivers, the very spot where the wow signal ended its long journey, is filled in with dirt and buried forever. In a matter of weeks, the work is done. The landscape is scraped clean, Where a giant 3-acre instrument once stood listening to the music of the spheres, there is now just flat, empty Earth, waiting to be sculpted into a new shape. A few years later, the transformation is complete. The site of the Big Ear is now the 7th hole of the Big Ear Golf Club. The land is covered in manicured green grass, pristine fairways, and sculpted sand traps. A small, discreet plaque near the clubhouse is all that remains to commemorate what once stood here. You are left standing on what was once hallowed scientific ground, the sound of a golf cart's motor replacing the hum of scientific machinery. The stark, almost surreal contrast forces you to ask a difficult and uncomfortable question. What does it say about our society's priorities when an instrument of potentially historic cosmic discovery, the very tool that captured one of history's greatest unsolved mysteries, is dismantled to make way for a recreational luxury like a golf course? It is a poignant and bitter end for a machine that represented one of humanity's grandest and most hopeful quests. A story that leaves you wondering what other priceless things we might be trading away for the mundane. The Big Ear is gone, its physical presence erased from the Ohio landscape, leaving behind only a plaque and a ghost. But you are about to discover that the true legacy of an instrument is not measured in steel and concrete, but in the ideas it inspires, and the questions it forces us to ask. While the telescope was silenced, the 72-second signal it recorded continues to echo, not in radio waves, but through the very fabric of the modern search for extraterrestrial intelligence. Its ghost became a guidepost. You find yourself now in the control room of a modern SETI facility, perhaps the Allen Telescope Array in California, or the Green Bank Observatory in West Virginia. The room is a world away from the clattering teletype printers of the 1970s. Here, you see silent, powerful servers, their glowing lights indicating the flow of immense torrents of data. Banks of monitors display complex spectral graphs and scrolling columns of data, the sky rendered not as a picture but as a living stream of information. The search is now faster, deeper, and more comprehensive than Jerry Eamon could have ever imagined. And yet, the spirit of his discovery is everywhere. You learn that the WOW signal, in the decades following its detection, became the benchmark, the gold standard for what a candidate ETI signal should look like. In a field that deals with boundless possibilities, the signal provided a concrete, tangible template. You listen to modern SETI researchers discuss their work, and you hear the characteristics of the WOW signal echoed in their search criteria. They are hunting for signals that are narrow-band, a clear sign of artificiality. They are focusing immense resources on the cosmic waterhole around the hydrogen line frequency. They are looking for signals that appear to come from a fixed point in deep space. In a very real sense, the global multi-billion-dollar enterprise of modern SETI is in large part a hunt for the WOW signal's siblings. The singularity of the signal, once its greatest weakness, became its most important lesson. The fact that it appeared once and was never heard again taught the scientific community a hard and valuable lesson. Alien signals may not be the continuous, persistent beacons we had hoped for. They might be transient, fleeting, and unpredictable. The old strategy of staring at a star for a while and then moving on was not enough. You had to be able to catch lightning in a bottle. Here, you discover a crucial, lesser-known detail about the technological evolution of the search. The greatest tragedy of the WOW signal was the delay. The signal was recorded on August 15th, but it wasn't discovered by Eamon until days later. By then, any chance of immediate follow-up was lost. Modern systems are designed specifically to prevent this from ever happening again. You watch the data stream on the monitors in the control room. Powerful algorithms, running on supercomputers, are analyzing the fire hose of information from the telescopes in real time. These algorithms are programmed with the WOW signal's profile. They are designed to spot a transient narrowband signal the instant it appears. If such a signal is detected, the system doesn't wait for a human to review the data days later. An alarm is triggered automatically. Within seconds, the software can command the primary telescope to break from its survey, lock onto the source, and track it across the sky. Simultaneously, alerts can be sent to other radio telescopes around the world, instructing them to point at the same coordinates. This rapid response protocol is a direct legacy of the Big Ear's famous near miss. Scientists have built a global net, a technological trap to ensure that the next one that got away does not in fact get away. The WOW signal therefore did more than just provide a tantalizing mystery. It fundamentally reshaped the methodology of the search. It forced a move from a passive archaeological model of sifting through old data to an active, responsive model of real-time detection and immediate verification. But as you stand in this gleaming modern facility, a challenging question begins to form in your mind. This entire sophisticated apparatus, this entire search philosophy, is built on the template of a single, 40-year-old, unconfirmed data point. Has the WOW signal, by setting such a high and specific bar for what a real signal should look like, inadvertently created a form of search bias? We are now exceptionally good at looking for narrow band signals near 1420 MHz. But what if other civilizations communicate in radically different ways? What if they use broadband signals, complex modulation schemes we can't recognize, or frequencies in parts of the spectrum we've dismissed as too noisy? What if they communicate with neutrinos or gravitational waves? By optimizing our search for one specific type of signal, are we effectively putting on blinders, making ourselves deaf to a chorus of other, stranger voices? The very event that so brilliantly illuminated the path for modern SETI may also have confined that path to a narrow, well-trodden lane, while a whole universe of other possibilities lies unexplored, just beyond our biased field of view. The legacy of the WOW signal is not just a philosophy, it's a catalyst for action. You've seen how it shaped the technology and strategy of the search. Now, you will witness the most powerful and direct attempt ever made to reawaken the ghost from Sagittarius. You find yourself in the era of a new audacious chapter in the human quest for answers, an initiative with the resources and the ambition to match the scale of the question. You are entering the world of breakthrough listen. It is the 21st century, and the search for extraterrestrial intelligence, long a fringe pursuit starved for funding, is reinvigorated. A $100 million 10-year initiative, funded by billionaire Yuri Milner and supported by a brain trust of the world's leading scientists, has begun the most comprehensive SETI survey in history. Their goal is to scan 1 million nearby stars and the 100 closest galaxies. But amidst this grand cosmic survey, one historical mystery holds a special place. One cold case is deemed worthy of a full-scale modern reinvestigation. The WOW signal. Your journey takes you to a remote valley in the mountains of West Virginia, a place so shielded from radio interference it's known as the National Radio Quiet Zone. Here, rising from the landscape like something from a science fiction dream, is the Robert C. Byrd Green Bank Telescope, the GBT. It is a masterpiece of engineering. A fully steerable radio dish over 100 meters across, taller than the Statue of Liberty, its gleaming white surface able to focus on any point in the sky with breathtaking precision. It is one of the most sensitive listening devices ever created by humanity. This is the instrument that Breakthrough Listen would turn into the ultimate ghost hunter. Between 2017 and 2018, the GBT was repeatedly aimed at the precise coordinates of the WOW signal's origin. You are there in spirit as this new high-tech hunt begins. This is not a simple retread of the searches from the 1970s. The technological leap is staggering. While the Big Ear monitored just 50 narrow channels, the GBT's advanced receivers, connected to a supercomputing cluster, can monitor billions of channels at once, covering a vast swath of the radio spectrum. Here you discover a fascinating lesser-known detail about the power of this modern search. The Breakthrough Listen team wasn't just looking for an exact repeat of the original signal. Their sophisticated software was designed to be a net that could catch a much wider variety of fish. It could search for signals that were drifting in frequency, as you might expect from a transmitter on a rotating planet. It could search for signals with complex digital modulations, not just a simple, pure tone. And it was so sensitive that it could have detected a signal many times fainter than the original WOW signal. It was the most powerful, comprehensive, and intelligent search for the signal ever conducted. If there was anything to be heard, a repetition, an echo, a weaker follow-up message, the GBT would hear it. You can feel the anticipation build as the observations are carried out. The great dish swivels silently, locking onto that haunted patch of sky in Sagittarius. For hours at a time, it soaks up every radio wave emanating from that direction, collecting an unimaginable flood of data, petabytes of it. which is then scoured by the project's powerful algorithms. This is the ultimate test. The ghost has been called out by name, challenged to appear before our most powerful technological eye. The results, when they are finally published, are as definitive as they are anticlimactic. After dozens of scans and the analysis of a mountain of data, the conclusion is announced to the world. They found nothing. No repeating signals. No faint echoes. No transmissions of any kind that could be attributed to an extraterrestrial technology. The silence from Sagittarius was deeper and more profound than ever, now confirmed by the most sensitive ear on the planet. The failure of this renewed high-tech hunt leaves you at a fascinating and frustrating crossroads. It eliminates the simple possibility that the WOW signal is a repeating, periodic beacon that we just needed a better telescope to find. That theory is now effectively off the table. But this definitive result does not solve the mystery. Instead, it sharpens the remaining possibilities into a stark, binary choice. You are forced to ask a difficult question. If even our most powerful, sensitive, and comprehensive search of the exact location finds absolutely nothing, what is the more likely conclusion? Does this profound silence strengthen the case for the one-shot beacon hypothesis? The idea that it was a singular, deliberate announcement that was never intended to be repeated? In this scenario, the silence is exactly what you would expect to find. Or, does the failure to find any trace of technological activity strengthen the case that the original signal was an almost impossibly rare natural phenomenon, a perfect storm of cosmic physics so unique that it has not recurred in 40 years and may never recur again? The Great Hunt's failure to find an answer has only made the question more pointed, leaving you to wonder whether the enduring silence is a sign of profound intelligence or just profound luck. You have grappled with the signal's intensity, its frequency, its duration, its location, and the enduring silence that followed. Each layer of the mystery has added to its complexity and its allure. Now you must delve into one of the most subtle, technical, and debated aspects of the event, a ghost in the data that is not about what was seen, but about what was missing. You are going to chase the Doppler ghost. You are familiar with the Doppler effect even if you don't know it by name. It is the reason why the siren of an approaching ambulance seems to rise in pitch and then fall as it passes you and moves away. The motion of the source relative to the observer changes the perceived frequency of the waves. This principle is not just for sound. It applies to all waves, including light and radio waves. In astronomy, it is a fundamental tool. By measuring the tiny shifts in the frequency of light from distant stars, we can tell if they are moving towards us, a blue shift, or away from us, a red shift. Now apply this principle to a hypothetical extraterrestrial signal. Imagine a transmitter on the surface of a planet orbiting a distant star. That planet is not stationary. It is spinning on its axis. It is also moving in a vast orbit around its sun. Our own planet, Earth, is also spinning on its axis and orbiting our sun. All of these complex motions relative to each other should impart a small but measurable Doppler shift onto any radio signal traveling between the two worlds. During the 72 seconds that the Big Ear was listening to the WOW signal, the Earth's rotation was carrying the telescope eastward at a speed of several hundred miles per hour. This movement should have caused the signal's frequency to drift or chirp in a predictable way. The frequency at the beginning of the observation should have been slightly different from the frequency at the end. It would be an incredibly small change, but it should have been there. A faint signature of our own planet's motion imprinted on the alien signal. This is where you uncover another profound and lesser-known puzzle within the data. When radio astronomers, years after the fact, meticulously analyzed the technical details of the detection, they found something baffling. The signal's frequency was incredibly, unnaturally stable. Over the full 72-second observation, there was no detectable drift. The signal was a pure, unwavering tone, a single note held with impossible perfection. The expected Doppler ghost, the signature of Earth's rotation, was nowhere to be found. This absence is a paradox that cuts in two different directions. On one hand, it seems to weaken the most common ETI scenario. If the signal came from a transmitter on a planet, why wasn't its frequency being affected by the complex dance of celestial mechanics? This lack of a drift has been used by some skeptics to argue that the signal must have had a terrestrial origin, as a local source would not exhibit the same kind of cosmic Doppler shift. On the other hand, the extreme stability of the signal makes it look even more artificial. Natural phenomena are rarely so constant. The signal's unwavering frequency is yet another characteristic that is difficult to explain through chaotic natural processes. So how can you explain this missing ghost? The most straightforward and most likely explanation is a mundane one: the instrument's limitations. The Big Ear's receivers had a frequency resolution of 10 kilohertz. The expected Doppler drift over 72 seconds would have been far smaller than that. It's entirely possible and even probable that the frequency chirp was there, but our equipment was simply too coarse, too primitive, to detect it. The ghost was present, but we were blind to it. But this mystery opens the door to more speculative and more fascinating possibilities. What if the lack of a Doppler shift wasn't an accident of our measurement, but a deliberate feature of the transmission? This leads you to a challenging and mind-bending question. Could the very lack of a Doppler shift be the most sophisticated message of all? Imagine a civilization so technologically advanced that they can not only send a powerful signal across light years of space, but they can also precisely calculate the recipient's motion. They would know the Earth's orbital path, its rotational speed, its axial tilt. They could then preemptively correct for the Doppler shift that we would perceive. They could actively alter their transmitted frequency, moment by moment, in just the right way to ensure that by the time the signal arrived at our moving telescope, the drift would be perfectly canceled out. The signal would arrive as a pure, stable tone, as if it were coming from a transmitter that was stationary relative to us. This act of Doppler correction would be a staggering technological feat, a form of cosmic marksmanship that demonstrates a profound mastery over physics. It would be a subtle, elegant, and powerful meta-message, a way of saying, "We are here, we see you, we understand your physics, and we can manipulate the fabric of space-time to make our message perfectly clear." You are left to wonder, is the missing Doppler shift simply an artifact of our own technological limitations, a sign of our inability to see the finer details of the event? Or is it the most sophisticated and subtle clue we have, a deliberate demonstration of technological prowess from a civilization that wanted to ensure their signal was not just heard, but recognized as a work of undeniable and breathtaking intelligence? You are left with a series of fascinating but unproven theories: the one-shot beacon, the message in the math, the ghost of a Doppler shift. Each one attempts to explain the signal's most maddening quality: its solitude, the fact that it happened once, perfectly, and then vanished forever. You have considered that the transmitter may have been turned off. You have considered that it was a fluke of nature. Now you must entertain another equally eerie possibility. What if the transmitter is still on, still broadcasting its powerful note, but it is simply no longer pointing at us? To understand this, you must transport yourself to a dark, stormy coastline on a moonless night. You are on a ship, lost in an endless churning sea. All is darkness and chaos. Then, for a brilliant, startling moment, a powerful beam of light slices through the blackness, illuminates your vessel, and then sweeps past, plunging you back into darkness. You have just seen the beam from a lighthouse. You know the lighthouse is still there, its lamp still lit. But its rotating beam is now pointing elsewhere, warning other ships on other parts of the sea. You are left in the dark, waiting, knowing that if you stay in this spot long enough, the beam will eventually come around again. Now apply this powerful analogy to the cosmos. You must now explore the interstellar lighthouse theory. Imagine, somewhere in the star-dense regions of Sagittarius, a civilization has constructed a beacon. But instead of broadcasting in all directions at once, an incredibly wasteful use of energy, they have channeled their power into a single, narrow, focused beam. This beam is attached to a slowly rotating mechanism, or perhaps the transmitter itself is on a celestial body that is naturally rotating. Like the lighthouse on the coast, this cosmic beacon is continuously sweeping its beam of radio energy across the vast ocean of the galaxy. The beam is always on, a persistent, unwavering signal, but any single point in its path, any single star system, will only be illuminated for a brief fleeting moment as the beam glides past. You can now replay the events of August 15, 1977, in this new context. For eons, this hypothetical beam has been sweeping its silent path across the Milky Way. On that summer night, the Earth, in its own inexorable orbit around the Sun, happened to drift into the beam's path. For 72 fleeting seconds, our solar system was bathed in the light of this artificial 1420 MHz signal, and the Big Ear, in an act of unbelievable cosmic serendipity, happened to be looking at the right place at the right time, with the right frequency settings to catch the flash. Then, just as the lighthouse beam sweeps past the lost ship, the cosmic beacon continued its slow, silent rotation. The beam moved on, leaving our solar system once again in radio darkness. This theory elegantly accounts for the signal's primary characteristics. Its power and artificial nature are explained as features of a deliberate beacon, and its singularity is explained perfectly. We have not heard it again, not because the source is extinct or silent, but because the lighthouse has not yet completed its full rotation. We are in the long, dark period between flashes. This raises a tantalizing and unknowable question. What is the period of the beacon's rotation? If its sweep is relatively fast, say once a year, then the fact we haven't detected it again deals a heavy blow to this theory. But what if its rotation is glacially slow? What if its year is equivalent to 100 of our years? Or 1,000? Or 1,000,000? If so, we could be waiting for a very, very long time for the light to return. The silence we are experiencing isn't an ending, but merely an intermission of unknown and potentially vast duration. We are the ship's crew, staring out into the darkness, wondering if we will survive long enough to see the next flash. This thought experiment forces you to confront a challenging question about your own significance in the cosmos. If we were, in fact, illuminated by such a beacon, does that imply a deliberate act of targeting, or was it a cosmic accident? In one scenario, a distant intelligence has identified our solar system as a place of interest, a potential cradle of life, and has deliberately swept us with their hello. This is a profoundly hopeful and terrifying thought. We have been noticed. But there is another, perhaps more likely possibility. The beacon may be part of a vast, indiscriminate survey. Its purpose may be to sweep across millions, even billions of star systems in a slow, methodical search pattern, without any prior knowledge of which ones harbor life. In this case, our 72-second illumination was a completely random event. We were just another house on another street that a searchlight happened to pass over. Our detection of the signal was not a sign of our importance, but a reminder of our cosmic mediocrity, one candidate among countless others. You are left on your ship in the cosmic ocean, staring in the direction of the long-vanished light, and you are faced with an unsettling ambiguity. Was that flash in the night meant for you, a sign that you are not alone? Or were you just a random piece of debris momentarily caught in a sweeping indifferent beam? You have no way of knowing. You can only wait in the darkness and listen. You have traveled the full circle of this great mystery. You have analyzed the data, explored the theories, met the man who found it, and mourned the machine that recorded it. You are left with one stubborn, irreducible, and profoundly important question that lies at the heart of the entire enigma. Why only once? If it was an intelligent signal, a genuine attempt at contact, the silence that followed is the most baffling part of the story. To confront this, you must now confront one of the most famous and unsettling ideas in all of science, the Fermi paradox. The paradox, first formulated by physicist Enrico Fermi, is simple. The universe is ancient and incomprehensibly vast. Our galaxy alone contains hundreds of billions of stars, many of which are billions of years older than our sun. Statistically, the conditions for life should be common. Intelligent, technological life should have arisen countless times. Some of these civilizations should have become interstellar. And yet, when we look out at the cosmos, we see nothing. We hear nothing. The universe, it seems, should be teeming with life, but it is utterly silent. Where is everybody? Fermi asked. This is the great silence. The wow signal is the one potential exception, the one possible crack in that wall of cosmic silence. But its status as a singleton, a one-time only event, makes it a frustrating and paradoxical piece of the puzzle. It does not resolve the Fermi paradox. It deepens it. It suggests that someone is out there, but they are not behaving in the way we would expect. You must now explore the cold, hard logic of a singleton signal and what its existence might imply about the civilization that sent it. Let's consider the first possibility. The silence is a sign of immense patience and perspective. This is the patient God scenario. You are dealing with a civilization that may be millions of years old. Their conception of time is likely as alien to us as their biology. For them, a human lifetime is a fleeting moment, and our entire recorded history is a blink of an eye. In this context, a conversation with a back and forth lasting thousands of years might seem absurdly fast-paced. They may operate on a different timescale entirely. They send their one-shot beacon or their sweeping lighthouse flash not as an invitation to chat but as a seed. They plant it in the sky and are content to wait for 10,000 years or 100,000 to see if anything grows. Their silence is not a sign of absence but a sign of a patience so profound it is indistinguishable from indifference. They have spoken once. The next move is ours, and they are in no hurry. Now, you must consider a darker possibility, one tied to the proposed solution to the Fermi paradox known as the Great Filter. This theory suggests that there is some evolutionary or technological barrier that is incredibly difficult for life to overcome. It could be the leap from single-celled to multi-celled organisms, the development of intelligence, or most ominously, a filter that lies ahead of us like self-destruction through nuclear war, climate change, or artificial intelligence. Most civilizations, the theory goes, hit one of these filters and are destroyed. In this grim context, the wow signal could be interpreted as a warning. It could be a desperate message in a bottle, sent by a civilization that was facing its own great filter. Perhaps they saw the end coming and wanted to let others know. Their 72-second message wasn't a hello, but a beware. Its singularity is explained by the simple, brutal fact that they were silenced before they could send another. They were snuffed out, leaving behind only this one, final, desperate cry. This leads you to the third, and perhaps most poignant and terrifying scenario, the tombstone. The signal was not a greeting from the living or a warning from the dying, but an echo from the dead. Imagine a civilization that knows its doom is inevitable. Its star is about to go supernova. Its planet's atmosphere is failing. As a final, defiant act of existence, they construct a great transmitter. They pour all their remaining energy and resources into a single, automated broadcast. It is a monument, a eulogy, a final testament to their time in the universe, screaming into the void for eternity. We were here. We lived. We mattered. The transmitter sends its powerful 72-second message and then falls silent as the civilization that built it perishes. The signal we received in 1977 was not a phone call. It was an automated message from a tomb. You are left to weigh these chilling possibilities, each a potential answer to the question of why only once. And this forces you to confront the final, challenging question of the signal's true nature. What is the more terrifying possibility? That the signal was a greeting from a living, godlike civilization that is still out there, has seen us, and has consciously chosen to remain silent, leaving us to our cosmic isolation, or that it was a final dying gasp from a civilization that is now extinct, a lonely voice from a galactic graveyard, a reminder that in the end, the great silence may claim us all. Your long journey is coming to an end. You have chased an echo through 40 years of science, speculation, and silence. You began on a quiet summer night in Ohio, beside a colossal listening ear. You stood with a volunteer astronomer in his study as he stared at a string of characters so anomalous, so perfect, that he could only describe it with a single breathless word. You have followed this ghost as it has been interrogated, analyzed, and pursued by some of the greatest minds and most powerful instruments on Earth. And now, after all this time, you find yourself right back where you started, in the presence of a profound and beautiful mystery. You have walked through the evidence. You have seen how the signal's staggering power, its laser-like narrowness, its duration, and its position at the sacred hydrogen line frequency make it a textbook candidate for a work of extraterrestrial technology. You have also seen how its confounding flaws, the single horn detection and above all its refusal to ever appear again, have left it in a state of scientific limbo. You have weighed the mundane explanations and found them wanting, built upon chains of improbable coincidence. You have seen the elegant comet theory rise and fall, dismantled by the unyielding facts of physics. You have entertained grand, speculative theories of cosmic lighthouses, patient gods, and dying civilizations. After all of it, the signal endures, unexplained. It remains to this day the single strongest candidate for an extraterrestrial signal ever recorded. It is a perfect anomaly, a ghost that has resisted every attempt at exorcism, a 72-second riddle that has stumped humanity for nearly half a century, and in a world of endless data, the original artifact remains a powerful, tangible icon of this mystery. Here you discover one last grounding detail: the original computer printout, the very page where Jerry Eamon circled 6EQUJ5 and wrote "Wow" in red ink, is not lost to time. It is carefully preserved by the Ohio History Connection, a sacred text of an unknown religion, a physical relic of a potentially transcendent event. You are left to contemplate the signal's true legacy. It is not a story with a neat conclusion. It offers no easy answers. Its power, you realize, is not diminished by this ambiguity but magnified by it. The WOW signal has become more than just a data point. It has become a cultural touchstone, a modern myth. It serves as a constant, humbling reminder of the sheer scale of our own ignorance. It is the ultimate ghost in the machine, a whisper that proves that the universe is not only stranger than we imagine, but stranger than we can imagine. This forces you to ask one final, all-encompassing question. After all the analysis, all the debate, and all the speculation, does the true power of the WOW signal lie not in what it might be, but in the questions it forces us to ask about ourselves? Perhaps its purpose was never to give us an answer about aliens, but to provoke a question about humanity. It is a cosmic mirror, reflecting our own hopes, our own fears, and our own desperate, profound desire to not be alone. The echo without a source forces us to listen more intently, to search more diligently, and to wonder more deeply about our own fleeting, fragile place in the vast, silent cosmos. The signal's ultimate message may be that the search itself, and the questions it makes us ask, is what truly matters. Tonight, we've journeyed through the enduring mystery of the WOW signal, a 72-second whisper from Sagittarius that has puzzled scientists for nearly half a century. We've explored its seemingly artificial nature, its power, its frequency, its narrowness, and the profound, unending silence that followed. We've weighed the theories, from mundane explanations like comets to speculative ideas of interstellar lighthouses and messages from the distant past. Yet after all this time, it remains an echo without a source, the most compelling piece of evidence that we may not be alone, and the most frustrating of cosmic cold cases. The signal forces us to ask, what is the meaning of a single, unrepeated sign? Was it a fluke, a warning, a greeting, or a tombstone? The answer continues to elude us, locked away in the silence between the stars. Thank you for joining me on this investigation. Your curiosity and willingness to explore the unknown are what keep these stories alive. Never stop questioning the unexplained. That's all for today. Stay curious, stay questioning, and I'll see you in the next file.